Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the cosmos stretches out like a soft blanket above your thoughts. Tonight, we're not staring straight at the stars or at the galaxies that hold them, but into the quiet spaces that lie between, the places that rarely get mentioned in the grand stories of the universe, the dark, nearly empty oceans of space where almost nothing seems to happen, and yet everything depends on them. Before we begin drifting outward, I wonder, where are you listening from tonight? Maybe you're wrapped up under a dim lamp or tucked into bed with the glow of your screen painting, little constellations on your wall. Maybe it's late and the world around you has gone still, leaving just the hum of your thoughts. Out there, beyond the walls of your room, beyond the air and clouds and even the solar system itself, space expands in every direction. And between all the shining islands of star, between the galaxies, lies something so vast, so silent, that even light seems to hesitate before crossing it. If you find this gentle journey soothing or interesting, or just a nice way to unwind after a long day, it would mean a lot if you gave it a like, or maybe subscribed. It helps this little corner of calm reach others who might also be searching for a quiet place to rest, while their mind keeps wandering. So settle in. Let your shoulders drop a little, slow your breathing, and imagine for a moment that the universe is opening up around you, not rushing or roaring, but expanding softly, like an inhale that never quite ends. When we look at pictures of galaxies, they often appear close together, bright spirals scattered across the black like glowing seashells. But those images are deceiving. The spaces between them are unimaginably wide. The nearest galaxy to our own, the Andromeda Galaxy, sits about 2.5 million light-years away. That means the light we see from it tonight left long before the first humans painted on cave walls. And that's not even far by cosmic standards. Between the clusters of galaxies, the gaps can stretch hundreds of millions of light-years across. Empty expanses where, for all our instruments can tell, there's almost nothing. But the word nothing can be tricky in science. When physicists talk about emptiness, they rarely mean complete absence. Even the darkest voids are laced with faint whispers of matter, energy, and radiation. Space between galaxies isn't pure vacuum, not really. It's more like an almost invisible mist of atoms, particles, and light, stretched thin by the expansion of the universe. For every cubic meter of that space there might be only 1 or 2 stray atoms of hydrogen, a density so low it makes the emptiest laboratory vacuum on Earth seem crowded. And yet, those atoms matter. They hold clues to what the universe is made of, how it formed, and how it continues to change. The space between galaxies is where cosmic history has left its fingerprints. Faint, cold, and scattered, but still there if you know how to look. Imagine standing in thought somewhere out there in that intergalactic darkness. No stars nearby, no planet under your feet. Just a black so complete it almost feels physical. The nearest galaxy would be a faint smudged glow, far too distant to cast any shadow. You'd be surrounded by nothing but the soft, ever-expanding fabric of space itself. It sounds lonely, but in a strange way it's also peaceful, because in that emptiness lies the structure of everything. Astronomers sometimes describe the universe as a kind of foam, with galaxies gathered along thin threads that stretch around vast empty regions called cosmic voids. These voids aren't just gaps. They are part of the universe's grand architecture. If you could step far enough back, if you could see the entire universe at once, it would look a bit like a 3-dimensional spiderweb made of light and gravity. The galaxies sit at the intersections of these threads, clustering together where the invisible filaments of matter cross. Between those intersections are the dark spaces, the in-between, where almost no galaxies live. This cosmic web wasn't always there. In the earliest moments after the Big Bang, matter was spread nearly evenly throughout space. Tiny fluctuations in density, just small differences in how much matter was in one spot compared to another, slowly grew under the pull of gravity. Over billions of years, those denser regions pulled in more matter, forming stars and galaxies, while the emptier regions became emptier still. The result is what we see today, great filaments of clustered galaxies wrapping around bubble-like voids that span hundreds of millions of light years. If you could drift through one of those voids, you'd find yourself in a place so empty it defies imagination. The temperature would hover just a few degrees above absolute zero, no nearby star to warm you, no sound because there's nothing for sound waves to travel through. The only light would come from the faint glow of distant galaxies, scattered like embers across an endless night. Occasionally, a single atom of hydrogen would drift past, maybe one every few meters if you're lucky. And yet, even here, physics hums quietly in the background. Photons from the cosmic microwave background, the leftover light from the Big Bang, still pass through. They've been stretched by the expansion of the universe until they glow faintly in the microwave range, too dim for eyes, but detectable by sensitive instruments. It's a faint, omnipresent reminder that even the emptier spaces still carry memory. There's something almost paradoxical about it. The vastness between galaxies seems to separate everything, and yet it also connects everything. The same expansion that creates the distance also ties all of space together. When galaxies drift apart, they're not moving through space so much as being carried along by the expansion of space itself. Like dots on the surface of a balloon as it inflates, the galaxies aren't flying away from a center. The space between them is simply stretching. The more it stretches, the faster it expands, and that means the more we look between galaxies, the more we're looking at the process that defines the universe's shape and fate. For much of human history, we didn't even know those gaps existed. The night sky seemed crowded, filled with stars. Only in the last century did we learn that most of the universe's volume is not filled with stars at all, but with darkness. Galaxies are like glitter sprinkled on the surface of a vast, invisible ocean. And the more we've learned about that ocean, the more we've realized it may hold the biggest mysteries of all. Some of those mysteries are familiar names now: dark matter, dark energy. Ideas that began as attempts to explain the space between. When astronomers measured how galaxies move, they found something strange. Galaxies within clusters orbit far too fast to be held together by the gravity of visible matter alone. There had to be something else, something invisible, filling the gaps, binding galaxies together with its unseen pull. That's how the idea of dark matter began. Whatever it is, it doesn't emit light, but it exerts gravity, and it's not rare. In fact, dark matter makes up most of the universe's mass. It weaves through the cosmic web like scaffolding, holding galaxies in place. But if dark matter pulls things together, something else pushes them apart. Observations of distant supernovae in the late 1990s revealed that the universe's expansion isn't slowing down as scientists expected, it's speeding up. That accelerating stretch is attributed to something we call dark energy. We don't know what it is. It might be a property of space itself, an inherent pressure that grows as the universe expands. Or it might be something even stranger, a new form of energy or field that fills the cosmos. Whatever it is, dark energy now dominates the universe, shaping the vast spaces between galaxies more than anything else. So when we talk about what lies between galaxies, we're really talking about the arena where dark energy does its work, where dark matter builds its scaffolds, and where the faintest whispers of ordinary atoms drift like dust motes in an immeasurable room. If you were to point a telescope at one of those dark patches of sky, a place that looks completely empty to the naked eye, and keep it there long enough, days, weeks, even months, light would begin to appear. The Hubble Space Telescope did this once, in a famous experiment called the Hubble Deep Field. From a patch of sky no larger than a grain of sand held at arm's length, it gathered light from thousands of galaxies, some so distant their light began its journey more than 13 billion years ago. What looked like emptiness turned out to be filled with entire universes of its own. But between those distant galaxies still lies far more space than light. Most of the universe, by volume, is made of the in-between, the intergalactic medium, the cosmic web, the dark matter scaffolding, and the stretching fabric of space-time itself. Galaxies, as dazzling as they are just the punctuation marks. The sentence of the universe is written in the spaces. As your thoughts drift through this idea, you might notice how quiet it feels. Thinking about these vast distances often brings a kind of stillness with it. It's not an emptiness that threatens, but one that soothes. Because in those impossible expanses lies a reminder of scale. The same universe that stretches trillions of kilometers between galaxies also fits inside the span of your imagination. You can hold it there, gently, without needing to fill it. Just space. Just the in-between. And as we move deeper into this exploration, that's where we'll stay for a while. Not among the crowded clusters of stars, but out here, in the dim, almost forgotten corridors of the cosmos. The regions where gravity's whispers and light's faint echoes still shape the story of everything. In a sense, every galaxy owes its existence to what lies between. Without the pull of dark matter, without the pressure of expanding space, without the faint gases that drift through the void, galaxies would never have formed. What we think of as nothing turns out to be the quiet architect of everything, and the more we study it, the clearer that becomes. The next time you look up at the night sky, try not to focus only on the stars. Instead, let your gaze rest on the dark spaces between them. That darkness isn't absence, it's the canvas of creation. It's where the universe hides its most patient work. And if you let your thoughts drift far enough, you might feel that same vastness reflected inside you. That quiet sense that between all the moments of life, between all the thoughts and breaths, there is also space. And that space too matters, because in the end, everything that is, everything that ever will be, is held together by what lies in between. When you start to imagine the space between galaxies, it's tempting to picture it as a kind of endless emptiness, a featureless gulf stretching on forever. But the more precisely we try to describe that gulf, the more complex it becomes. To say the distances are large doesn't quite capture it. Even the word vast feels too small. These are stretches of space so enormous that ordinary comparisons simply stop working. Take the distance between our own Milky Way and its nearest large neighbour, Andromeda. As we mentioned earlier, that's about 2.5 million light-years. A light-year is the distance light travels in 1 year, roughly 9.5 trillion kilometres. It's a unit so big we often stop trying to visualise it. But to understand the scale between galaxies, it helps to at least try. Imagine light, the fastest thing in existence, streaming through space at nearly 300,000 kilometres per second. Even at that speed, it takes more than 2 million years to cross the gap between just these two galaxies. Every time you look up and see the faint smudge of Andromeda in the night sky, you're seeing light that left when early human ancestors were still walking the savannas of Africa. And that's just the nearest large neighbour. Most galaxies are much farther apart. If we could step back far enough to see several galaxies at once, they would look like islands scattered across an invisible ocean. But this isn't an ocean of water or air. It's space itself stretching, expanding, carrying the galaxies along with it. In this ocean there is no shore, no true centre, no edge where it ends. Wherever you stand in the universe, it expands away from you equally in all directions. The distances between galaxies are increasing, not because the galaxies are moving through space, but because space itself is growing between them. This is one of the hardest ideas for the human mind to grasp. We're used to movement meaning travel, a car crossing a road, a bird flying across the sky. But galaxies drifting apart aren't moving through a background of space. The background itself is stretching. Every second, the fabric of the universe adds a little more distance between distant galaxies. That's why the farther away a galaxy is, the faster it seems to be moving away. It's not racing through space like a rocket. the space between us is simply expanding. Astronomers can actually measure this stretching by looking at the light from distant galaxies. When light travels through expanding space, its wavelength gets stretched too, a phenomenon called redshift. The more distant the galaxy, the more its light is shifted toward the red end of the spectrum. By measuring that shift, scientists can calculate how far away the galaxy is and how fast space has expanded since the light left it. It's like looking at a photograph that's been slowly stretched over billions of years and learning about the expansion of the universe from the way the image has warped. Through that light, we've learned that galaxies aren't just scattered randomly. They form groups and clusters connected by thin filaments of matter, like the threads of a web. Between these clusters are immense regions of emptiness, the cosmic voids. These are the truly distant spaces, sometimes hundreds of millions of light years across, where there are hardly any galaxies at all. They're not completely empty, but they're as close as the universe gets to a pure vacuum. It's difficult to talk about something that big in familiar terms. If you could somehow shrink the Milky Way to the size of a small coin, the nearest comparable galaxy would be several cities away. The next cluster of galaxies, the Virgo cluster, would be thousands of kilometers beyond that. And the cosmic voids between them? They would stretch across entire continents. These are distances that make even our most ambitious spacecraft seem motionless. The fastest probe ever built by humans, the Parker Solar Probe, moves at about 700,000 kilometers per hour. At that speed, it would take more than 40 billion years to reach Andromeda, longer than the current age of the universe itself. So when we talk about the space between galaxies, we're talking about distances that are, for all practical purposes, unreachable. These are places we can only explore through light, through mathematics, and through the patient accumulation of data. And yet, these distances define the shape of everything. The universe looks the way it does because of the spacing between galaxies, not just their clustering. If galaxies were packed more tightly together, the sky would glow with their light, and darkness would be rare. If they were farther apart, there might not be enough gravitational pull to form large structures at all. The universe's balance, its quiet architecture, depends on just how much distance lies between these great collections of stars. It's strange to think that most of the cosmos is space, not matter. If you could gather up every star, every planet, every grain of dust, every atom of gas and compress it all into one place, the universe would still be almost entirely empty. The galaxies themselves, enormous as they are, take up an almost negligible fraction of the universe's total volume. Most of everything is distance. Most of existence is the in-between. That distance is not uniform either. The distribution of galaxies across the sky is uneven. In some regions, galaxies cluster so densely that they form superclusters, gravitationally bound groups of clusters stretching across hundreds of millions of light years. Between those superclusters lie the great cosmic voids. These voids aren't just dark, they have a slightly different physical environment. The temperature, density, and even the background radiation shift slightly. Space here is thinner, colder, quieter. If you could drift into one, the nearest galaxy might be so far away that its light would look like a faint, motionless dot, no brighter than a distant star. And yet, there's motion everywhere. Even across these vast distances, galaxies are not completely still. They move under the combined influence of gravity, drifting toward each other within clusters, pulled by the unseen threads of dark matter. Some are slowly falling together, like the Milky Way and Andromeda, which are on course to merge billions of years from now. Others are drifting apart forever, carried by the expansion of the universe faster than gravity can reel them back. When you imagine these distances, it's easy to forget that light itself takes time to travel. Every time you look at a distant galaxy, you're looking back in time. The farther away it is, the older the image. Some of the faintest smudges we see through powerful telescopes show us the universe as it was only a few 100 million years after the Big Bang. The light from those galaxies has been travelling for more than 13 billion years, crossing the expanding space stretched and cooled by time. That means that in a sense, much of the universe we see no longer exists in the form we're seeing it. The galaxies have moved, merged, changed. Their light is ancient. Between us and those galaxies lies intergalactic space. Thin, cold, nearly empty, but not entirely devoid of matter. In the early universe, this space was filled with hydrogen gas, left over from the Big Bang. Over billions of years, much of that gas fell into galaxies, where it formed stars. But some remained behind, stretched thin between galaxies, ionized by the radiation from early stars and quasars. This intergalactic medium, as astronomers call it, is still out there, filling the voids with a faint ghostly presence. When light from distant quasars passes through it, it leaves subtle fingerprints in the spectrum, faint absorption lines that tell us about the gas's composition and temperature. Those fingerprints allow astronomers to map invisible matter across vast distances. They show that even the emptiest regions are connected by a tenuous network of gas and plasma, forming the skeleton of the universe. Where the gas is slightly denser, galaxies form. Where it's thinner, voids remain. So even the enormous distances between galaxies aren't truly barren. They're woven with filaments of gas, dust, and dark matter, so faint they're almost impossible to see directly. As you think about those distances, it's worth pausing to remember that space itself is not static. The rate of expansion, what we call the Hubble constant, determines how fast galaxies move away from each other. For decades, astronomers have tried to measure it precisely, but the results vary slightly depending on how it's measured. The debate isn't just about numbers, it's about what those numbers say about the universe's age, its composition, and its fate. If expansion continues to accelerate under the influence of dark energy, then the distances between galaxies will grow so large that, in the far future, most galaxies will drift beyond the observable horizon. Their light will never reach us again. The night sky will grow emptier. Future observers, living in a galaxy far in the future, might look out and see only darkness, unaware that billions of other galaxies ever existed. That thought might sound lonely, but it's part of the quiet beauty of cosmic perspective. The universe isn't built for human comfort. It simply is vast, cold, expanding. And yet within it, life found a way to observe and wonder. Somewhere in one tiny galaxy, in one narrow band of time, a species evolved that could measure light across billions of years and try to make sense of distances too large to travel. Thinking about this doesn't have to feel isolating. It can be grounding. The spaces between galaxies aren't just voids, they're context. Without the emptiness, there'd be no structure, no contrast, no room for galaxies to exist. Space isn't just what lies between things. It's what allows things to be separate, to have shape, to exist at all. The more we study those immense separations, the more we realize how fragile and interconnected everything is. Galaxies might seem isolated, but they were born from the same early universe, shaped by the same forces, bound by the same invisible threads of gravity. Across distances that light itself struggles to cross, the laws of physics remain perfectly consistent. Hydrogen still behaves like hydrogen. Gravity still pulls. The same patterns repeat at every scale, from the swirl of a storm on a planet to the spiral arms of a galaxy. And somewhere in all that, there's a quiet kind of reassurance. The distances between galaxies might be beyond comprehension, but they don't break the continuity of the universe. They define it. They're part of its rhythm, the slow pulse of expansion and separation that has been unfolding for more than 13 billion years. So as we drift further into this story, keep that sense of scale in mind. Between every shining cluster lies the real body of the universe, the distance itself. It's not nothing, it's not empty. It's the silent stage upon which everything else performs. And the more we learn to listen to that silence, the more it begins to tell us. When scientists began mapping the universe in detail, they didn't start out looking for patterns on the larger scales. The early goal was simple enough: to find out where galaxies were, how they were arranged, and how fast they were moving. Telescopes gathered light from tens of thousands of galaxies, each one marked on a cosmic chart as a tiny point. At first, the data looked random, like scattered dust across an empty table. But as the surveys grew, something unexpected began to appear. Faint, repeating structures. Galaxies weren't evenly spread. They were arranged in long, interconnected strands, forming clusters, filaments, and knots that wound their way through enormous voids. The universe wasn't a smooth sea of matter. It was textured, patterned, and surprisingly organized. This pattern became known as the cosmic web. The term sounds almost poetic, but it's entirely literal. On scales of hundreds of millions of light years, matter in the universe forms a web-like network. Galaxies, clusters, and superclusters are strung along filaments of dark matter and gas, while between them lie enormous empty spaces. It's as if the universe spun its own delicate web from gravity and time, weaving threads of matter that stretch from one cosmic region to another. To understand why this happens, we have to return to the early universe, the period just after the Big Bang. Back then, space was hot, dense, and nearly uniform. There were no galaxies, no stars, no clusters, just an expanding soup of particles and radiation. But even in that smoothness, there were tiny imperfections. Some regions were slightly denser than others, maybe 1 part in 100,000. Over billions of years, gravity amplified those differences. The denser areas attracted more matter, growing heavier and drawing in nearby material, while the emptier areas became emptier still. Out of that slow gravitational dance, the large-scale structure of the universe took shape. Computer simulations show this process beautifully. When cosmologists feed the early conditions of the universe into powerful models and let them evolve according to the known laws of physics, the results are astonishing. The simulated universe develops a web-like pattern that closely matches what astronomers observe through telescopes. The filaments and clusters appear naturally as gravity pulls matter together along invisible threads of dark matter. The voids open up between them, vast hollows surrounded by glowing walls of galaxies. What began as a nearly uniform fog of particles becomes a cosmic tapestry, the largest structure ever discovered. Dark matter plays the starring role in this formation. Although it's invisible, it makes up most of the universe's matter content, about 5 times more than the ordinary matter that forms stars and planets. Dark matter doesn't interact with light or electromagnetism, but it does respond to gravity. It clumps together under its own pull, forming halos and filaments that serve as the scaffolding of the cosmic web. Ordinary matter, the gas and dust that eventually form galaxies, collects along these structures, settling into the gravitational wells carved out by dark matter. In this way, the visible universe is a kind of shadow of the invisible one. Galaxies trace the outlines of dark matter's unseen architecture. Astronomers have found clever ways to map these hidden structures. One method uses the bending of light, called gravitational lensing. When light from distant galaxies passes near massive regions of dark matter, its path bends slightly, distorting the image. By studying these distortions across large areas of the sky, scientists can reconstruct where the invisible mass lies. When they do, the resulting maps show the same familiar pattern, a web of filaments connecting clusters of galaxies across billions of light years. The structure is so consistent that it's sometimes called the backbone of the universe. If you could see the cosmic web with your eyes, it would be one of the most breathtaking sights imaginable. Picture an enormous 3-dimensional lattice, glowing faintly in places where galaxies gather, fading into transparency as the filaments stretch away into the void. Some filaments span hundreds of millions of light years, thin as threads but strong enough in gravitational terms to shape entire clusters. The intersections, or nodes, where several filaments meet, are where the most massive structures form, superclusters containing thousands of galaxies. Between them, empty voids open up like vast dark bubbles, each one millions of light years across. One of the most famous maps of this structure comes from the Sloan Digital Sky Survey, an ambitious project that has catalogued millions of galaxies. When the data is plotted in 3 dimensions, it reveals a structure that looks remarkably organic. The filaments twist and branch like neural networks or the veins of leaves. Some scientists have even compared the large-scale structure of the universe to the pattern of connections in a human brain. It's a strange coincidence, but an evocative one. 2 systems, one cosmic, one biological, both forming networks of connections shaped by underlying rules of growth and balance. Despite its immensity, the cosmic web is incredibly delicate. The density of matter in its filaments is still extremely low, far lower than any vacuum we could create on Earth. The gas that flows along those filaments is so thin that a single cubic meter might contain only a few atoms. Yet, over scales of hundreds of millions of light years, that faint presence adds up. It carries enough mass to influence the motion of galaxies and to act as a bridge between clusters. The filaments also serve as the highways of cosmic evolution. Gas flows along them into galaxy clusters, fueling star formation and feeding supermassive black holes. Some astronomers think of the web as a kind of circulatory system for the universe, constantly redistributing matter and energy. Without those flows, galaxies might have run out of material to form new stars billions of years ago. Instead, the cosmic web keeps them supplied, ensuring that the universe remains dynamic even as it grows older. It's not just matter that moves through the web, radiation and energy travel along it too. When distant quasars and galaxies emit light, that light passes through the filaments, picking up subtle signatures from the gas and plasma. By studying those signatures, scientists can measure the temperature, density, and composition of intergalactic space. These faint traces form a kind of record of how the universe has evolved. They tell us that the cosmic web isn't static. It changes slowly over time as galaxies form, merge, and exhaust their fuel. The filaments themselves shift as dark matter continues to shape the overall geometry of space. As we observe deeper into the universe, and therefore further back in time, we can see earlier versions of this web taking shape. The most distant galaxies we've found lie along primitive filaments that were still forming only a few 100 million years after the Big Bang. These early structures were smaller and less defined, but the pattern was already there. Gravity had begun its patient work, sculpting the universe from near uniformity into complexity. The cosmic web we see today is the result of that process running uninterrupted for more than 13 billion years. There's something quietly humbling about that. The same fundamental forces that shape the orbits of planets and the behaviour of falling apples also shape the structure of the entire cosmos. Gravity, acting slowly and relentlessly, built the universe's largest patterns from the simplest beginnings. It didn't require intention or design, only time and the laws of physics. When we study these vast structures, we often measure them in light years, megaparsecs, or other units so large they lose intuitive meaning. But what those numbers really describe is the accumulated effect of countless tiny interactions, particles pulling on one another across unimaginable spans of distance. The web exists because every bit of matter in the universe is tugging, ever so slightly, on every other bit. The universe, for all its size, is interconnected. If you think about that long enough, it starts to change the way you picture emptiness. The spaces between galaxies are not blank gaps, they're parts of a continuous whole. The web connects every galaxy, every cluster, even every atom of intergalactic gas, through gravity and the shared history of expansion. You could travel in any direction for billions of light years and still be moving along the same vast network of connections. There's no outside to it, no separate region where the web stops. it fills the observable universe entirely. The cosmic web also provides clues about the universe's ultimate fate. As dark energy drives expansion, the filaments are slowly stretching. Over billions of years, galaxies within clusters will remain bound together by gravity, but the spaces between clusters will grow wider. The web will thin out, its strands pull taut until, eventually, the distant filaments fade beyond the horizon of visibility. The large-scale structure will remain, but it will become more diffuse, quieter, slower. In a sense, the web is both the skeleton of the universe and its slow heartbeat. For now, though, we can still observe its grandeur. With instruments like the James Webb Space Telescope and deep surveys across radio, X-ray and optical wavelengths, we're mapping more of the cosmic web than ever before. Some of the most recent observations have even detected faint glows of gas along the filaments themselves, the first direct glimpses of the material that binds the cosmic structure together. Seeing those delicate threads of hydrogen stretching between galaxies is like seeing the bones beneath the universe's skin. It reminds us that even the spaces that appear dark are part of something larger, something structured and alive in its own slow gravitational way. When you imagine that vast web, it can be comforting to think of it as a kind of cosmic balance. The bright regions, galaxies, stars and nebula, are the visible expressions of structure, but they exist only because of the dark framework that supports them. Without the filaments of dark matter, galaxies would drift apart like scattered dust. Without the voids, there would be no contrast to define the clusters. The universe's beauty comes from that interplay, matter and emptiness, connection and separation, light and darkness. It's not a web in the human sense, of course. There's no centre, no edge, no purpose woven into its threads. But when you look at the maps and simulations, the resemblance is uncanny. The universe seems to have found a natural geometry, one that repeats across scales from the smallest subatomic networks to the largest cosmic ones. Whether that similarity is coincidence or some deeper reflection of physical law is a question still open. But it's hard not to feel a certain quiet awe when you realize that the pattern that defines galaxies also shapes clouds, rivers, even neural pathways. The universe repeats itself in form, if not in detail. And as you imagine those glowing filaments stretching through the dark, it's worth remembering that we're part of them. Our galaxy sits on one of those threads, connected by gravity to others across unfathomable distances. The atoms in your body were forged in stars that trace their origins back through billions of years of cosmic structure. Every element, every particle, every breath you take is tied to that web. You're not standing outside it, observing from afar. You're within it, a small expression of the same cosmic pattern. The next time you look at the night sky, think of it not as a collection of isolated points, but as a single structure stretching across all of existence. Every star, every galaxy, every speck of light is part of the same web, bound together by invisible threads of gravity and time. The spaces between may seem empty, but they're alive with connection. And as we move further into the story of what lies between galaxies, we'll see that those connections, the dark matter, the gases, the fields and the forces, are what hold the universe together. Because in a universe built mostly of emptiness, the web is what gives it shape. It's what turns endless distance into structure, what transforms randomness into order. And it's what reminds us that even in the most silent stretches of space, something invisible is still holding everything in place. If the cosmic web forms the structure of the universe, then the great voids are its open spaces, the quiet rooms between the walls. They're the most expansive regions in existence, and also the loneliest. When astronomers first began to realize that such enormous gaps existed, it surprised almost everyone. For a long time, the universe was imagined as a kind of uniform field of galaxies, spread more or less evenly across space. But as the maps improved and the data deepened, there were these empty spots, sometimes hundreds of millions of light years wide, where almost nothing seemed to be. The more we looked, the more those voids dominated the picture. It turned out that most of the universe's volume isn't filled with galaxies at all. It's made of these vast dark hollows. A cosmic void is not like the empty space between stars within a galaxy. Those distances are large by human standards, but small in comparison to the separations between galaxies themselves. A void is a region where galaxies are simply scarce. There might be a few lonely ones scattered throughout, but they're spread over such enormous distances that, from any one of them, the rest of the universe would look painfully remote. The light from the nearest neighbouring galaxy could take tens or even hundreds of millions of years to arrive. These are the quietest neighbourhoods in all of creation. The largest known voids are colossal structures with names that sound almost poetic in their understatement. The Bhuta's void, the local void, the Eridanus supervoid. Each of them is an ocean of near-nothingness, surrounded by the walls and filaments of galaxies that define the cosmic web. The Bhuta's void, for example, is roughly 330 million light-years across. Inside it are only a few dozen galaxies. To put that in perspective, in a region of that size elsewhere in the universe, you might expect to find tens of thousands. It's an absence so pronounced it almost demands explanation. For a long time, astronomers weren't sure what could create such enormous gaps. Over time, computer simulations of cosmic evolution helped provide an answer. As the universe expands, regions that start out slightly less dense than average tend to lose matter to their surroundings. Gravity pulls material toward the denser areas, the filaments and clusters, leaving the lower density regions even more depleted. Over billions of years, those small differences amplify, creating deep voids surrounded by dense walls. In this way, the great voids are not flaws in the universe's design. They're a natural consequence of how gravity and expansion work together. The universe builds its structure by separating fullness from emptiness, creating contrast on the grandest possible scale. From the edge of a void, the view would be extraordinary in its simplicity. Look one way and you'd see the crowded filaments, strings of galaxies glowing faintly, gathered into clusters, shining against the dark. Turn the other way and you'd see almost nothing at all. No stars, no visible galaxies, just blackness extending so far that your eyes would never find an end point. It would be like looking into the deep ocean at night, the sense of scale so overwhelming it becomes hard to imagine any boundary. The temperature there would be close to the cosmic background, about 2.7 degrees above absolute zero. That's colder than any vacuum chamber we can make on Earth. There's no sound, no wind, no dust drifting in the air because there's no air. Only the faint hum of radiation left over from the Big Bang, stretched into microwaves by the expanding universe. And yet, even this near-perfect emptiness isn't completely empty. Between the galaxies in a void, there are stray atoms, mostly hydrogen and helium, along with the occasional particle of dark matter. The density is so low it's almost meaningless to measure in ordinary terms. In some of the emptiest regions, you might find one atom in every 10 cubic meters. That's a vacuum so extreme that if you filled a room with it, it would take centuries for a single atom to wander from one side to the other. Still, those atoms are real, and they matter. They help astronomers trace how gas moves through the cosmic web and how galaxies at the edges of voids evolve differently from those in crowded regions. Galaxies that live near the boundaries of voids tend to be smaller, bluer, and richer in gas. With fewer gravitational neighbours tugging on them, they evolve more slowly, forming stars over longer periods of time. It's as if the emptiness itself grants them a quieter, more leisurely existence. Deeper inside the voids, isolated galaxies sometimes appear as faint, irregular shapes, strange, lonely systems with little structure. They drift through a darkness so complete that they may never encounter another large galaxy. In these places, cosmic time feels different. Everything happens on scales so vast and so slow that even the idea of change starts to lose meaning. Some researchers study voids not for what they contain, but for what they reveal. Because these regions are dominated by the effects of expansion, rather than by the local pull of gravity, they act as natural laboratories for testing cosmological theories. The way light travels through a void, the way it bends or stretches, carries information about the universe's overall composition, how much dark matter, dark energy, and normal matter there is. Voids also help test the accuracy of general relativity on the larger scales. If gravity behaved differently across such enormous distances, the shape and growth of the voids would betray it. So far, the observations match Einstein's equations remarkably well, but each new survey looks deeper, refining the picture. The size and distribution of voids can also tell us about the universe's history. In the early cosmos, when matter was still nearly uniform, small ripples in density started to grow. Those fluctuations, recorded in the cosmic microwave background, are the seeds from which today's voids and filaments grew. By comparing the patterns of those early ripples to the structure of modern voids, astronomers can check how the universe evolved over billions of years. It's a bit like studying the rings of a tree to understand how it grew, except the tree is the entire universe, and its rings stretch for hundreds of millions of light years. Every void is unique. Some are spherical, others irregular and twisted, shaped by the surrounding filaments that enclose them. They can merge, forming larger voids over time, or fragment as clusters shift around their edges. The boundaries are not sharp walls, but gradual transitions where the density of galaxies increases. Even in the largest voids, faint filaments of gas and dark matter thread through, connecting one edge to another. These faint traces link the emptiest regions back to the cosmic web, reminding us that even the most isolated spaces are still part of the universal whole. In some ways, voids are the universe's most honest regions. They are what happens when gravity and expansion are allowed to do their work without interference. Where there is matter, gravity binds and shapes. Where there is little matter, expansion takes over, stretching space until it thins into near nothingness. It's a balance, the push and pull of two opposing tendencies. Gravity gathers, expansion disperses, and the voids are the result of that delicate equilibrium. To get a sense of how pervasive these regions are, consider this. If you picked a point at random in the universe, chances are you'd find yourself inside a void. That's how dominant they are. Galaxies and clusters make up the walls and filaments that surround them, but the voids fill most of the volume. The luminous parts of the universe, the galaxies that we can see through telescopes, are like the foam on the crest of an unimaginably vast wave. The rest, the deep troughs and open water, is the emptiness in between. There's a quiet irony here. The places we can see most clearly, the galaxies, are the exceptions. The rule, the dominant reality of the cosmos, is absence. But that absence isn't meaningless. It's a necessary part of the structure. Without the voids, the filaments wouldn't stand out. Without emptiness, fullness couldn't exist. The universe's beauty lies in that contrast, not just in what's there, but in what isn't. Astronomers sometimes use the term cosmic web void network, a phrase that captures both the emptiness and the structure that defines it. The voids and the web are inseparable. Where the filaments curve, the voids form around them. As one grows, the other adjusts. Over billions of years, this balance shapes the large-scale geometry of everything. It's a process that continues even now. The universe is still expanding, still deepening its voids, still drawing matter into clusters. Slowly, quietly, the pattern evolves. When we think about these enormous spaces, there's a temptation to imagine them as silent in some existential sense. Lifeless, beyond reach, indifferent. And maybe they are. But there's another way to think about them. The voids are not just places where nothing exists, they're where potential resides. The emptiness is full of possibility, not in a mystical sense, but in a physical one. It's the stage upon which cosmic evolution unfolds. It allows galaxies to move, light to travel, expansion to occur. Without empty space, there would be no motion, no change, no time as we know it. Even the most profound silences of the universe are not absolute. Radiation from the early cosmos still fills them. Neutrinos, the lightest and most elusive of particles, pass through them by the trillions every second. Occasionally, a lonely photon crosses the void, travelling unimpeded for billions of years before finding an instrument sensitive enough to notice it. To that photon, the void is simply the path home. There are times when astronomers point their instruments at one of these regions and see nothing at all. No galaxies, no clusters, no sources of light. And yet, when they look in other wavelengths, faint signals emerge. X-rays from distant quasars, radio waves from intergalactic gas, gamma rays from ancient cosmic events. All of these pass through the voids, tracing their contours in ways our eyes can't see. The voids may be dark, but they're transparent. They let the universe's oldest light pass freely, carrying information across unimaginable distances. It's easy, when thinking about all this, to forget the human scale. To us, even the closest star beyond our sun feels impossibly far. Yet the distances between galaxies, and especially the stretches within the great voids, make those stellar separations seem tiny. Our entire galaxy could fit thousands of times over inside one of the larger voids. These are not regions we will ever visit or map directly in detail. They belong to the scale of the cosmos itself, too vast to traverse, too slow to change in any way we could witness. Still, knowing they exist changes how we think about the universe. It reminds us that emptiness is not nothingness, and that space itself is an active participant in the story of creation. The voids show us that even in the absence of matter, the universe continues to evolve, continues to shape itself. Their quiet persistence gives meaning to everything else. When you look at the night sky and see the dark patches between stars, remember that those dark areas aren't truly dark at all. They're filled with distances that, on larger and larger scales, stretch into the great voids that make up most of the universe. What seems like a small gap between pinpoints of light is the same kind of space that separates galaxies, clusters, and superclusters. The same pattern repeats again and again across all scales. There's a kind of peace in realizing that. The universe, for all its apparent chaos, has structure. Even its emptiest regions follow rules. Gravity, expansion, and time work together in a quiet, consistent rhythm. The galaxies flow around the voids like currents around deep basins, shaping one another as they go. It's not a process we can rush or observe unfolding in real time, but we can imagine it. We can picture the slow deepening of the cosmic hollows, the patient stretching of space, the delicate balance of forces that have been at play for more than 13 billion years. So the great voids, far from being forgotten corners of the cosmos, are among its most important features. They are the background against which everything else stands out. They are the silence that makes the music of galaxies audible. And though they may seem empty, they're part of the same continuous universe that produced stars, planets, and eventually us. In the grand picture, we're inhabitants of the spaces between, living within one tiny filament. Looking outward into the darkness that defines our cosmic home is not an empty darkness. It's the space that gives meaning to light. It's what allows galaxies to breathe and the universe to expand. And as we drift further into understanding what lies between them, we begin to see that even the most silent stretches of space are still part of something deeply connected, steady, and alive. If you were to look out into the universe and count everything you could see, from the brightest galaxies to the faintest clouds of gas, you might assume that what you're seeing is what exists. But that's not how the universe works. Almost everything we can observe, the stars, the planets, the dust and nebulae, the shining arcs of galaxies across deep space, makes up only a small fraction of what's really there. Most of the universe is invisible. It doesn't glow, it doesn't reflect, and it doesn't absorb light in any way that we can detect. It's something else entirely, and we call it dark matter. The name sounds mysterious, but it's mostly practical. Dark, because it doesn't emit or interact with light. Matter, because it exerts gravity and has mass. What makes it truly strange is that it appears to be the framework around which the visible universe is built. Without dark matter, galaxies as we know them couldn't exist. Their stars would drift apart, their structures would unravel, and the cosmic web itself would collapse. It's the hidden thread that holds the universe together, binding everything in place while remaining unseen. The story of how scientists came to suspect this invisible material existed began almost a century ago. In the 1930s, an astronomer named Fritz Zwicky was studying a cluster of galaxies in the constellation Coma. By measuring how fast those galaxies were moving, he could estimate the total mass needed to keep the cluster bound together by gravity. But when he compared that mass to the amount of light coming from the galaxies, the numbers didn't match. There wasn't nearly enough visible matter to explain the motion. Something unseen was providing extra gravitational pull. He called it dunkle Materie, dark matter. At first, few people paid much attention. The idea seemed speculative, and there wasn't much evidence beyond a handful of calculations. But in the decades that followed, more clues appeared. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford made precise measurements of how stars move within galaxies. If a galaxy's mass came only from its visible stars and gas, the stars near its outer edges should move more slowly than those near the centre, just as planets farther from the Sun orbit more slowly. But Rubin's data showed something else entirely. The stars on the outskirts were moving just as fast as those near the centre. It was as if an invisible halo surrounded each galaxy, adding enormous amounts of unseen mass. Those results were confirmed again and again in galaxy after galaxy. The pattern was unmistakable. There was far more matter than could be accounted for by what we could see. This unseen mass didn't just lurk inside galaxies, it stretched between them, connecting entire clusters in great halos that overlapped and merged into a vast invisible web. The more astronomers looked, the clearer it became that dark matter wasn't a minor addition, it was the main ingredient. Today, the evidence for dark matter comes from many directions. The way galaxies rotate, the way clusters move, the bending of light through gravitational lensing, the patterns in the cosmic microwave background, all of them point to the same conclusion. Roughly 85% of all matter in the universe is dark matter. Ordinary matter, the stuff that makes up everything we can touch, see, and measure directly, accounts for only a small remainder. In other words, most of the cosmos is made of something we can't see, something we don't yet understand, but which shapes every visible thing. The most striking part of that realization is how invisible doesn't mean inactive. Dark matter doesn't shine, but its gravity sculpts the universe. When scientists simulate the evolution of the cosmos using the laws of physics, they find that dark matter forms the backbone of structure formation. It gathers first, clumping under its own gravity into enormous halos. Ordinary matter then falls into these halos, cooling and condensing to form stars and galaxies. The visible universe traces the shape of dark matter's skeleton. If you could somehow remove all the dark matter, everything luminous would simply drift apart into chaos. But what exactly is it? That remains one of the most challenging questions in modern physics. There are many possibilities, none confirmed. Some theories suggest dark matter is made of particles similar to those in the standard model of physics, but much heavier and slower to interact. So-called WIMPs, or weakly interacting massive particles. Others propose lighter particles, like axions, which could behave more like waves than particles. There are also ideas involving sterile neutrinos, primordial black holes, or even entirely new fields that don't fit into our current understanding of physics at all. Each possibility carries its own predictions, and for decades physicists have built experiments to search for them. Deep underground, detectors shielded from cosmic rays wait for rare collisions between dark matter particles and atomic nuclei. sensitive telescopes scan the sky for signs of dark matter particles annihilating or decaying into detectable radiation. So far, no definitive signal has been found, though the search continues with ever more precision. The absence of direct detection hasn't weakened the case for dark matter. It's only deepened the mystery of what it truly is. Even without knowing its exact nature, we can still trace its presence. When light from a distant galaxy passes near a massive object, gravity bends it, a phenomenon known as gravitational lensing. The effect works even if the mass is invisible. By mapping how background light is distorted across large regions of the sky, astronomers can build detailed maps of where dark matter lies. Those maps show the same web-like structure seen in galaxy distributions, filaments connecting clusters, wrapping around vast voids, forming a continuous network that extends as far as we can see. These dark filaments are enormous, stretching across hundreds of millions of light years, yet they're incredibly faint. Most of their mass exists in diffuse halos, invisible to normal telescopes. Occasionally, astronomers detect a faint glow of gas or X-rays along them, evidence of ordinary matter drawn into dark matter's gravitational wells. These glimpses confirm what simulations predict. The universe is bound together by an invisible scaffold, and we are living inside one of its threads. Even our own galaxy, the Milky Way, is cocooned in a vast halo of dark matter. It's not confined to the disk where the stars lie, but extends hundreds of thousands of light years beyond the visible edges, blending gradually into intergalactic space. This halo shapes the orbits of stars and satellites, dictates how the galaxy rotates, and influences how nearby galaxies move. The Earth, the Sun, and every star you can see are all moving through this unseen sea of dark matter, surrounded by it constantly, though we can't feel it. One of the most intriguing things about dark matter is how it interacts, or rather, how it doesn't. It seems to feel only gravity. It doesn't absorb or emit light, and it barely, if ever, collides with itself or with normal matter. That means dark matter particles can pass right through entire galaxies without slowing down, forming diffuse halos rather than compact clumps. Because of this, the structure of dark matter is remarkably stable over cosmic time. While stars burn out and galaxies merge, the underlying dark matter web remains largely intact, evolving slowly as the universe expands. There's an elegance to this invisibility. It reminds us that not all things that matter can be seen. The cosmos depends on something hidden, subtle, and patient, a kind of quiet gravity that holds the visible world together. The stars and galaxies that light up the sky are, in a sense, decorations draped over an invisible framework. We're used to thinking of darkness as absence, but here, darkness is structure. Dark matter also has a curious relationship with the other great unknown of the universe, dark energy. While dark matter pulls things together, dark energy pushes them apart. The two forces act in opposition, shaping the large-scale geometry of the cosmos. Where dark matter's gravity slows expansion locally, dark energy's pressure accelerates it globally. The balance between these two unseen influences determines how the universe grows, how it will age, and perhaps even how it will end. The story of dark matter, then, isn't just about invisible mass. It's about the unseen harmony between attraction and expansion. On one side, gravity quietly binding galaxies, on the other, space itself stretching outward. Somewhere between those two lies the present-day universe, a snapshot of equilibrium billions of years in the making. Scientists continue to look for ways to see dark matter indirectly. Some experiments search for faint signals from cosmic collisions that could produce gamma rays or other energetic particles. Others use new techniques like mapping how clusters of galaxies move in relation to the cosmic web. Each approach is like feeling along a dark corridor, tracing shapes by touch rather than sight. We may not have found dark matter yet, but we can feel its presence everywhere we look. There's a subtle irony in how well we understand something we can't see. we can measure its effects with extraordinary precision, even though the thing itself remains invisible. We know how much there is, where it lies, how it shapes light and motion, and how long it's been around. We just don't know what it's made of. It's a little like hearing the melody of a song without ever finding the instrument that plays it. If dark matter could somehow glow, even faintly, the night sky would be utterly transformed. Instead of scattered pinpoints of light, we'd see glowing filaments stretching in every direction, a vast, intricate network linking every galaxy. The spaces between galaxies would no longer look empty. They'd shimmer with the faint light of the dark matter web. But the universe hides this structure from us, leaving only gravity to reveal its shape. In recent years, observations have confirmed that dark matter's influence extends even beyond the visible boundaries of galaxies. Streams of stars in our own Milky Way, remnants of smaller galaxies torn apart by tidal forces, trace the contours of the dark halo. Their motions are like breadcrumbs, revealing the unseen mass around them. These cosmic relics provide some of the best evidence for how dark matter sculpts galaxies from within. Even galaxy collisions, those grand and violent events that reshape entire star systems, follow dark matter's choreography. When two galaxies merge, their stars and gas collide, but their dark matter halos pass through one another almost untouched. The visible galaxies crash and deform, while the invisible halos slide together, merging slowly into a new, larger structure. In this way, dark matter guides the long-term evolution of galaxies, determining their size, shape, and destiny. The bullet cluster, a famous example observed by astronomers, shows this process in action. Two galaxy clusters have collided, sending their hot gas smashing together and producing a bright X-ray glow. But when scientists mapped the gravitational field using lensing, they found that most of the mass wasn't in the gas. It was offset, aligned with the galaxies themselves, not with the colliding plasma. That's because the dark matter passed straight through, unaffected by the collision. It's one of the clearest demonstrations that dark matter is a distinct, non-interacting substance, separate from the ordinary matter we know. When we look at all this evidence together, a picture emerges. The universe is not made primarily of what shines, but of what doesn't. The luminous parts are just the visible peaks of a much deeper landscape. Beneath every galaxy, every cluster, every cosmic filament lies the quiet gravitational foundation of dark matter. It's the hidden architecture upon which the visible universe is built. And yet, for all its importance, dark matter remains silent. It doesn't reveal its presence directly. It doesn't emit, absorb, or reflect light. It doesn't respond to magnetic fields or nuclear forces. It simply exists, invisible but inescapable. Its only voice is gravity, and through gravity, it speaks across the entire cosmos. As you think about this, you might notice how the concept of dark matter changes the way we imagine space itself. The universe isn't just a scattering of galaxies across emptiness. It's a woven structure with invisible filaments binding everything together. Every star you see, every planet, every atom of dust is held in place by this unseen web. The universe isn't floating apart, it's hanging in a vast gravitational tapestry that stretches from one end of the cosmos to the other. Even here, on Earth, we're part of that invisible structure. Every moment, countless dark matter particles, whatever they are passing through you, through the ground beneath your feet, through the entire planet, without leaving a trace. They've been doing so for billions of years, indifferent to our presence, yet vital to our existence. Without them, there would be no galaxies, no stars, no planets, no life. It's strange, but comforting in a way, to realize that the universe is mostly made of something unseen. We live surrounded by mystery, supported by forces that work quietly, invisibly, without ever drawing attention to themselves. It's a reminder that the foundation of things doesn't always announce itself. Sometimes, the most essential parts of reality are the ones that never make a sound. If dark matter is the unseen hand that holds the universe together, then dark energy is the invisible breath that pushes it apart. It's the quietest force imaginable, but it dominates the cosmos. Wherever galaxies drift, wherever light travels, this subtle energy stretches space itself, expanding the distances between everything that exists. It doesn't roar, it doesn't rush, it simply continues, slow, steady, unstoppable. For much of human history, the universe was thought to be static. The stars, the galaxies, the sky itself, all fixed in place, eternal, unchanging. Even when we learned that galaxies were moving, expanding outward from a common beginning, the assumption remained that this expansion must be slowing down. Gravity, after all, pulls things together. Every galaxy's mass should tug on every other, gradually decelerating the outward motion. That was the expectation, until the late 1990s when astronomers measuring distant supernovae found something entirely different. The light from those supernovae didn't match a slowing universe. It matched one that was speeding up. The expansion wasn't weakening, it was accelerating. Space itself was stretching faster than before, as if some hidden pressure were pushing it outward. The discovery was so unexpected that even the researchers hesitated to believe it. But over time, the evidence grew stronger. Observations of the cosmic microwave background, the distribution of galaxies, and the behavior of large-scale structures all confirm the same truth. The universe isn't just expanding, it's doing so at an ever-increasing pace. The name given to the cause of that acceleration is dark energy. Like dark matter, it's a placeholder, a label for something we don't yet fully understand. What we do know is that it makes up about 70% of the universe's total energy content. That means the majority of what exists isn't matter at all, but this mysterious energy woven into the fabric of space itself. The simplest explanation comes from Einstein's own equations of general relativity. When he first formulated them in 1915, he included a term called the cosmological constant, a kind of built-in energy of empty space that could counteract gravity and hold the universe static. Later, when astronomers discovered that the universe was actually expanding, Einstein supposedly called the constant his greatest blunder. But decades later, that same idea returned, not as a mistake, but as an answer. The cosmological constant, reinterpreted, could explain dark energy. It represented a property of space itself, an energy density that remains constant even as space expands. That idea is deceptively simple. Empty space, according to this model, isn't really empty. Even in the absence of matter and radiation, the vacuum has energy. And as the universe expands, the amount of space increases, so the total energy increases as well. This causes the expansion to accelerate. It's as if the universe is being gently inflated by its own emptiness. To many physicists, that sounds elegant, but it also raises profound questions. Why does the vacuum have energy at all? How much should it have? Quantum mechanics tells us that even the emptiest vacuum is never truly empty. It's filled with fleeting fluctuations, virtual particles that appear and vanish too quickly to observe directly. These fluctuations should contribute to the vacuum's energy density. The problem is that when you calculate how much energy this quantum vacuum should contain, the result is absurdly large, many orders of magnitude greater than what we actually observe. In fact, it's one of the biggest discrepancies in physics. Somehow, the true value of dark energy is vastly smaller than theory predicts. No one knows why. Other theories try to describe dark energy as something dynamic rather than constant, a field that evolves over time, changing its influence as the universe ages. In those models, dark energy might not be an intrinsic property of space, but a new form of energy or particle we haven't yet discovered. Some even speculate that dark energy could eventually weaken or reverse, changing the ultimate fate of the cosmos. For now, though, all observations point to the same outcome. Dark energy is real, pervasive, and steady. It fills every cubic meter of space, from the depths of intergalactic voids to the corners of our own galaxy. It doesn't cluster or gather like matter does. Instead, it acts uniformly everywhere, stretching the universe evenly in all directions. Its strength is so slight that it has no noticeable effect on small scales. It doesn't pull at you, or at the Earth, or even at the galaxy. But on the larger scales, where distances reach billions of light years, its influence dominates everything. To understand what that means, imagine the universe as a vast elastic fabric. Galaxies are not flying through this fabric, they're embedded in it, carried along as it stretches. The stretching itself is what we call expansion. Dark energy is what drives that stretching. Over billions of years, it's been increasing the separation between galaxies, pushing them apart faster and faster. The galaxies themselves don't feel this motion. Locally, their own gravity still binds them together. But the space between clusters of galaxies keeps widening. The result is a universe whose large-scale structure is expanding while its local systems remain intact. If we could somehow watch this process unfold in real time, it would look like a slow drift, the distances between galaxies growing imperceptibly year by year. After millions of years, the change would become measurable. After billions, dramatic. Every moment, dark energy adds just a little more space between every distant point. Over very long timescales, this gentle acceleration has profound consequences. As the expansion continues, galaxies that are now visible will drift farther away. Eventually, their light will be redshifted so much that it fades from view entirely. Billions of years from now, distant galaxies will slip beyond the cosmic horizon, the limit beyond which light will never reach us, no matter how long we wait. To future observers, the universe will appear much emptier than it does today. Only the closest galaxies, gravitationally bound to one another, will remain visible. Everything else will recede into an unreachable darkness. This future is sometimes called the era of isolation. It's a slow fading of cosmic connection, caused not by destruction, but by expansion. Space itself grows so vast that communication between distant regions becomes impossible. It's not a violent end, just a quiet drifting apart, the universe expanding into solitude. There's something almost paradoxical about dark energy. It's the dominant force in the universe, yet it's also the least tangible. It doesn't pull or push in any way we can directly sense. It acts everywhere at once, equally and invisibly. It doesn't concentrate. It doesn't vary. It simply exists as part of the background reality. That calm persistence, that quiet steadiness, is part of what makes it so mysterious. For cosmologists, studying dark energy is an exercise in subtlety. It can't be measured directly, but its effects can be inferred through careful observation. One approach is to map the large-scale distribution of galaxies over time. The rate at which structures form and grow is influenced by the balance between gravity and dark energy. Another method looks at distant supernovae, standard candles, whose brightness can reveal how quickly the universe has expanded at different epochs. By comparing data from different eras, scientists can reconstruct how the expansion rate has changed. So far, all the evidence supports an accelerating universe. There's a quiet elegance to the way these measurements come together. Each independent line of evidence, from supernovae, from the cosmic microwave background, from Barion acoustic oscillations, from gravitational lensing, all point to the same picture. The cosmos is dominated by a smooth, persistent energy that resists compression and drives expansion. It acts not like ordinary matter, but like a property of the vacuum itself. Even though dark energy defines our universe, it has no clear origin story. We can trace matter and radiation back to the Big Bang. We can explain how atoms and galaxies formed, but dark energy simply seems to have been there all along. Some cosmologists wonder if it might be connected to the energy of the quantum vacuum, while others suggest it could arise from extra dimensions or fields predicted by string theory. There are even proposals that dark energy is an illusion, that our interpretation of general relativity needs refinement on cosmic scales. But until new evidence appears, the simplest explanation remains the most widely accepted. Dark energy is the energy of space itself. Thinking about that can be unsettling. Space is not nothing. It has weight, energy, and behavior. It's dynamic, capable of stretching and growing. When we say the universe is expanding, we're not talking about galaxies moving through a pre-existing void. We're talking about the void itself changing. Every second, new space comes into being. Dark energy is the quiet reason why. When you imagine that process, it's easy to think of it as something happening far away between distant galaxies at the edge of the observable universe. But the truth is, it's happening everywhere, even here. The space between you and the nearest star is expanding too, just so minutely that local gravity cancels the effect. The same expansion that stretches the universe on the grandest scales is also present in the smallest gaps between objects. It's an omnipresent property of reality itself, imperceptible locally but decisive globally. There's an odd piece in that thought. The universe isn't rushing apart in a dramatic explosion. It's expanding softly, gradually, like a deep, unending breath. Every galaxy, every cluster, every stretch of empty space participates in that same quiet motion. There's no edge to it, no center, no sound, just the steady unfolding of the cosmic fabric. When cosmologists model the far future, they find that dark energy will likely continue to dominate. The current era, in which galaxies still gather and stars still form, is temporary. As time passes, expansion will dilute the matter content of the universe, making gravity's influence weaker and weaker on large scales. Eventually, only the structures bound by their own gravity, galaxies and local clusters, will remain intact. Beyond them, the universe will grow darker, colder, and emptier. That doesn't mean it ends, it just becomes quieter. The stars will burn out, galaxies will fade, and space will continue to expand. It's not a catastrophic finale, but a gradual transformation into stillness. The universe will persist, just in a state where change happens so slowly that it becomes almost imperceptible. Dark energy, for all its mystery, may be the reason we have this particular kind of universe. One that lasts, one that grows, one that allows structure to form before slowly letting it drift apart. Without it, the cosmos might have collapsed long ago under its own gravity, or expanded too quickly for galaxies to form at all. Somewhere in the balance between attraction and expansion, the conditions for everything we know were set. Sometimes, when scientists talk about dark energy, they describe it as the most important discovery we don't understand. It defines the present and future of the universe, but we have no clear theory for it. The deeper we look, the more it reminds us how limited our knowledge still is. But there's something beautiful about that limitation. The fact that such a quiet, invisible force shapes everything gives the cosmos a kind of calm humility. It doesn't need to announce itself, it just is. So as we imagine the spaces between galaxies, filled with dark matter's hidden threads and stretched by dark energy's quiet expansion, we begin to see the universe not as static or empty, but as alive in a slow, continual transformation. Every moment, space itself is growing, carrying galaxies with it like leaves on a rising tide. It's a process so vast and so gentle that it feels less like motion and more like breathing. The universe's own rhythm, steady and eternal. Light has always been our messenger. It's the one thing that connects us to everything else in the universe. Every star we see, every galaxy we've ever photographed, every faint glimmer recorded by a telescope, all of it comes to us through light. For most of human history, it was the only thing we had to understand the cosmos. We can't travel to the stars, we can't touch distant galaxies, but we can collect the light that left them millions or even billions of years ago. That light is the universe's story, written in a language of wavelengths and colours. But even light has its limits. It travels fast, faster than anything else can move, yet the universe is vast enough to stretch that speed to its breaking point. When light leaves a distant galaxy, it begins a journey through expanding space, across distances so immense that they change the light itself. By the time it reaches us, it has aged, its energy has faded, its colour has shifted, and its message carries the marks of time. Much of what we call darkness is not the absence of light, but light that has travelled too far to remain visible. Every photon that reaches your eyes tonight has lived a long and complicated life. The light from your lamp or your phone screen may be milliseconds old, but the light from the stars is ancient. The nearest star beyond the Sun, Proxima Centauri, is more than 4 years away at light speed. When you see its faint red glow, you're seeing it as it was 4 years ago. The light from the Andromeda Galaxy left about 2.5 million years ago, when early humans were just learning to use tools. The light from the most distant galaxies we can observe began its journey more than 13 billion years ago, long before the Earth existed. It's a strange thing to realise that when you look into the night sky, you're looking through time. The farther you gaze, the older the universe you see. Each photon is a time traveller, carrying information about what the cosmos used to be. But the journey those photons make isn't easy. Space isn't a fixed stage. It stretches as the universe expands, and as it stretches, it drags the light with it. This stretching changes the wavelength of light, shifting it toward the red end of the spectrum, what astronomers call redshift. It's not because the light itself is slowing down. It always travels at the same speed. It's because the space it's moving through is expanding. Each wave of light gets stretched as the universe grows, and by the time it reaches us, its energy has decreased. A photon that left a galaxy as visible light might arrive billions of years later as infrared or even microwave radiation, too faint for our eyes to see. This is one reason why so much of the universe is invisible to us. Light that began its journey long ago has been stretched so much that it no longer falls within the range of visible wavelengths. To detect it, we need telescopes that can see beyond what our eyes can, into the infrared, the radio, and the microwave. Instruments like the James Webb Space Telescope, the Atacama Large Millimeter Array, and the Cosmic Background Explorer all look for light that's been transformed by time and distance. What they find is that even the darkest parts of the sky glow faintly when you look deep enough. The fading of light over distance isn't just a matter of redshift. There's also the simple fact of spreading out. Imagine a flashlight beam travelling through space. As it moves away from the source, the same amount of light covers a larger and larger area. The intensity drops, becoming weaker the farther it goes. For a galaxy billions of light years away, even its brightest stars are reduced to a whisper of light by the time they reach us. Most galaxies we see are just a few photons per second striking the detectors of telescopes. Every one of those photons has travelled for billions of years, dodging gas, dust, and the slow expansion of the universe. Many others never make it at all. Intergalactic space, though incredibly empty, isn't completely transparent. Scattered clouds of gas, mostly hydrogen, drift between galaxies, and those atoms can absorb or scatter light. The effect is subtle but cumulative. Over billions of light years, these faint traces of matter act like a filter, removing specific wavelengths and dimming the light that passes through. This absorption leaves a fingerprint in the spectrum, known as the Lyman alpha forest, a dense pattern of absorption lines that tells astronomers about the structure and composition of the universe between us and the source. Through those patterns, we can learn where the gas lies, how dense it is, and how it's moving. Even light that's partially lost tells us something. The way it fades carries information about what it passed through. The darkness between galaxies, then, isn't silent. It's a record of the journey light has taken. Sometimes entire regions of the universe seem to disappear behind curtains of opacity. In the earliest epochs, before the first stars and galaxies formed, the universe was filled with neutral hydrogen that absorbed nearly all ultraviolet light. Astronomers call this the cosmic dark ages, a period when the universe was transparent to radio waves but opaque to visible light. Only after the first stars ignited, flooding space with radiation, did the hydrogen become ionized, allowing light to travel freely. That reionization marked the end of cosmic darkness, and the beginning of the luminous universe we can observe today. Yet even now the limits of visibility remain. Beyond a certain distance, light from galaxies is stretched so much by expansion that it fades into the infrared. Beyond that, it becomes microwave radiation, the same ancient glow we detect as the cosmic microwave background. That faint radiation, nearly uniform in all directions, is the oldest light we can see, released when the universe was about 380,000 years old. Before that moment, the cosmos was too hot and dense for light to travel freely. The photons we observe today from that era have been travelling for over 13 billion years, their wavelengths stretched by a factor of 1,000. They're not visible light anymore. They're a cold whisper from a time when atoms were first forming. In a way, every observation we make is bounded by that horizon, the surface beyond which light hasn't had time to reach us yet. The observable universe is defined not by where space ends, but by how far light has travelled since the beginning of time. Anything farther away exists, but we can't see it. Its light is still on the way, trapped by the relentless expansion of space. As the universe grows older, that horizon changes. More regions slip beyond reach. Light lost to distance becomes light lost to history. For astronomers, this fading of light is both a limitation and a gift. It prevents us from seeing everything, but it also reveals how the universe works. The way light stretches, dims and changes tells us about expansion, about the age of galaxies, about the motion of stars and gas. Every shift in wavelength is a measurement of time itself. Sometimes, the loss of light becomes a kind of map. When we look at galaxy clusters billions of light years away, the redshift shows not only distance, but the rate of cosmic expansion at different times. Each layer of faintness, each degree of dimming, adds another data point in the story of how the universe grows. The further we look, the slower the pace of time appears. Distant galaxies seem frozen in their youth, their light arriving long after the events themselves have passed. In the deepest images taken by telescopes like Hubble, a single patch of sky can reveal thousands of galaxies, some of them so faint that only a handful of their photons reach the detector after weeks of exposure. Those photons travelled through the stretching fabric of space for nearly the entire age of the universe. When we collect them, we're catching the last remnants of ancient light, barely hanging on after billions of years of redshift. It's humbling to realise that our understanding of cosmic history depends on such fragile signals, faint flickers that have crossed unimaginable distances to reach us. But light doesn't only fade with distance, it also bends, slows and scatters. Gravity itself can distort it. When light passes near a massive object, a galaxy cluster for instance, its path curves. This bending gravitational lensing can magnify distant galaxies, allowing us to see farther than we otherwise could. But it can also scatter light, blurring and stretching it. Sometimes the universe acts like a giant lens, focusing light from the farthest galaxies through the gravity of those in between. Without this natural magnification, some of the most distant sources would remain invisible forever. Still, no matter how powerful our instruments become, there will always be light we can't reach. Some of it is hidden by dust within galaxies. Some of it has been absorbed by intervening gas. Most of it has simply been stretched beyond detection, lost to the universe's own expansion. Over time, even more will slip away. As dark energy continues to accelerate the growth of space, distant galaxies will recede faster and faster. Their light will redshift beyond any possible detection. The cosmos will grow darker, not because it's dying, but because its light is drifting beyond reach. In that far future, only local galaxies, those bound to us by gravity, will remain visible. The rest of the universe will fade into blackness. Future astronomers, if any remain, might look up at the night sky and see only a handful of galaxies, unaware that billions once surrounded them. They'll live in a smaller, quieter universe, their horizon closing in as light continues to slip away. It's a haunting thought, but not a sad one. The universe isn't losing its light so much as it's carrying it farther away. Every photon that leaves a star continues forever, even if no one sees it. It keeps travelling through space, stretched by expansion, diluted by distance, but still moving at the speed of light, still bearing the imprint of its origin. Somewhere, even now, light from the first stars is still on its way, crossing voids that have grown 1,000 times larger than when that light began. When we think about the spaces between galaxies, we tend to picture darkness, vast, cold emptiness. But much of that darkness is light in disguise, light too old or too stretched for our eyes to see. The universe isn't truly dark. It's filled with ancient light we can no longer perceive. It's everywhere, faint, constant, invisible. The glow of the cosmic microwave background, the infrared hum of distant dust, the radio murmur of dying galaxies, all of it adds up to a background brightness that never entirely goes away. Every moment the Earth moves through this ocean of faint radiation, photons from the early universe pass through us constantly unnoticed. They've been travelling since long before our planet formed, carrying the afterglow of creation itself. If you could see them, the sky would never be black. It would shimmer faintly with the cooled light of 1 billion lost suns. The loss of light over distance teaches us something subtle about the nature of perception. We think of seeing as instantaneous, as a direct encounter with the present, but in cosmic terms, sight is memory. Every photon that reaches us is a record of the past. The farther we look, the older that memory becomes. There is no way to see the universe as it is right now. We can only see it as it was. The deeper our view, the older the story we read. That realization gives the cosmos a strange intimacy. When you look up at the night sky, you're not seeing something distant in time and space. You're seeing the light that chose this exact moment to arrive. Every star you see has been waiting billions of years to be noticed. Every photon that touches your eyes completes a journey that began long before you existed. In the end, light lost to distance isn't really lost. It's transformed. It changes as the universe changes, carrying history within it. Even as it fades beyond visibility, it leaves traces. A shift in temperature, a whisper in radio waves, a pattern in the background glow. Through those traces we can still hear the universe speaking. It's quieter now than it once was, but not silent. The light is still out there, travelling endlessly through the growing spaces between galaxies, each photon a tiny messenger of what once was and what still continues, just farther away than we can see. And as we drift through this expanding sea of ancient light, we begin to understand that darkness is not absence, but the accumulation of distance. What seems empty is only the place where light has travelled too far to remain bright. The universe, even in its dimmest corners, is still glowing, softly, invisibly, eternally. Between the galaxies, across the vast distances where the light fades and the voids stretch almost endlessly, there exists something faint, almost forgotten, yet absolutely essential to the universe's story. It's not a place, not a structure, but a presence, thin, invisible, and all-encompassing. Astronomers call it the intergalactic medium. It's the substance that fills the spaces between galaxies, a ghostly blend of atoms, ions, and plasma, that drifts through the cosmic web like a mist so diffuse it might as well not be there, yet it is everywhere. When people imagine outer space, they tend to picture a perfect vacuum, an absolute emptiness. And it's true that compared to any environment on Earth, intergalactic space is staggeringly empty. But emptiness, in cosmic terms, is never truly empty. Even in the darkest regions between clusters, even in the heart of a great void, there are still atoms scattered through space. Hydrogen, helium, and trace elements, remnants of the Big Bang, still fill the universe. It's just that they're spread so thinly that we rarely notice them. In every cubic meter of intergalactic space, there might be only 1 or 2 atoms, sometimes fewer. It doesn't sound like much, but when you add it up over billions of light years, it becomes an ocean of matter, invisible to our eyes, but vast beyond imagination. The intergalactic medium, often shortened to IgM, is one of the universe's quietest components. It doesn't shine brightly like stars, it doesn't cluster into galaxies, and it doesn't form planets. Yet it holds most of the universe's normal, or baryonic, matter. The kind of matter made of protons and neutrons. Galaxies, despite their brilliance, contain only a small fraction of the total ordinary matter that exists. The rest floats between them in this great diffuse reservoir of gas. For a long time, astronomers didn't realize how important this medium was. When they counted up all the visible matter in stars, gas, and galaxies, the numbers didn't match what cosmological theories predicted should exist. There was a large portion of matter missing, not the mysterious dark matter that outweighs everything else, but ordinary atoms that seemed to have vanished. The answer turned out to be that they hadn't vanished at all. They were simply too spread out and too hot to detect easily. They were hiding in the spaces between galaxies. Over time, new instruments allowed astronomers to find this missing material. They looked not for light emitted by the intergalactic gas, but for light that passed through it. When light from a distant quasar, one of the brightest objects in the universe, travels across intergalactic space, it encounters patches of hydrogen gas. Each cloud absorbs specific wavelengths, leaving a pattern of dark lines in the quasar's spectrum. This pattern, known as the Lyman alpha forest, acts like a barcode for the universe. Each line represents a separate cloud of gas at a different distance, allowing scientists to trace how the intergalactic medium is distributed through space. What they found was remarkable. The intergalactic medium isn't uniform. It forms filaments and threads that mirror the cosmic web of dark matter. It's denser along the filaments where galaxies cluster, and thinner inside the voids. The same structure that defines the arrangement of galaxies also shapes the invisible gas between them. Everywhere we look, the pattern repeats, a faint echo of the universe's earliest architecture, preserved in the whisper-thin medium between worlds. The composition of this gas tells a story of cosmic evolution. Most of it is hydrogen, the simplest and most abundant element, left over from the Big Bang. A smaller fraction is helium, produced in those same first few minutes of cosmic history. But mixed within are trace amounts of heavier elements, oxygen, carbon, nitrogen, and iron. Those elements couldn't have come from the Big Bang. They were forged inside stars in the hearts of galaxies and then carried outward by supernova explosions and galactic winds. Over billions of years, galaxies have been slowly polluting the intergalactic medium with the products of their life cycles. In that sense, the space between galaxies isn't just empty. It's enriched with the ashes of countless generations of stars. Some of that material drifts forever, remaining part of the faint gas that stretches across the cosmos. Some of it eventually falls back into galaxies, fueling new waves of star formation. It's a cycle, slow and delicate, but continuous. The intergalactic medium is like the bloodstream of the universe, carrying matter from one region to another, connecting galaxies through invisible flows of gas. One of the most fascinating aspects of the intergalactic medium is its temperature. You might think that space this empty would be uniformly cold, but it isn't. The gas between galaxies can vary from a few thousand degrees to millions of degrees, depending on where it lies. Near galaxies and along filaments, Where matter is more concentrated, gravity compresses the gas and heats it through shocks and collisions. In these regions, the intergalactic medium becomes a tenuous plasma, glowing faintly in ultraviolet and X-ray wavelengths. Deeper in the voids it cools, drifting closer to absolute zero. Across the entire universe, this gas forms a temperature map, a patchwork of warmth and cold that mirrors the cosmic landscape. Detecting that faint warmth took decades of effort. Ordinary telescopes can't see it, because the gas is far too diffuse to emit visible light. Instead, astronomers use space-based observatories that can detect ultraviolet and X-ray radiation. The data they collect is almost ghostly, weak, featureless glows that require long exposures and sensitive instruments to reveal. But once the pattern emerges, it's unmistakable. The intergalactic medium fills the universe like a soft veil, glowing faintly where galaxies gather and thinning out toward the empty regions. In the last few decades, scientists have discovered an especially important part of this medium, known as the warm-hot intergalactic medium, or WIM for short. It's the portion of intergalactic gas heated to temperatures between 100,000 and 10 million degrees Kelvin. Despite its heat, it's incredibly thin, a few atoms per cubic meter at most. Yet when astronomers accounted for all the matter in the universe, the WIM turned out to contain the missing half of the baryons that had long eluded detection. The invisible became accounted for, not by changing theory, but by learning to see more softly. When you picture this vast, diffuse gas, it's hard to find a direct analogy on Earth. It's too thin to behave like air, too hot to behave like space dust. It's a plasma in the most tenuous possible state, a medium between being something and almost nothing. And yet, it's everywhere. Every galaxy you've ever seen, every star and planet is surrounded by it. The intergalactic medium connects all of them, a continuous but almost intangible ocean. If you could somehow float through it, the journey would be imperceptible. There would be no wind, no pressure, no sound. The gas is too thin to carry vibrations. You wouldn't even feel its presence. But if you could see with instruments sensitive enough to detect a single photon of X-ray emission, you would realize you were surrounded by a faint glow, the residue of star formation, supernovae, and cosmic heating. The medium would appear like a vast, dim fog of ionized gas, stretching endlessly in every direction, punctuated by the distant glimmer of galaxies floating within it. This invisible fog is not static. It moves, flows, and evolves with time. Along the filaments of the cosmic web, gas streams into galaxies, feeding their growth. At the same time, galaxies push gas back out into the intergalactic medium through powerful winds driven by supernovae or active black holes. This exchange of matter is called the cosmic Barion cycle. It's how galaxies breathe, drawing in fuel, converting it into stars and exhaling enriched gas back into the universe. The intergalactic medium is the environment where that breath disperses. Even though we can't see this gas directly, its influence is everywhere. It affects how galaxies form and how they die. It determines how quickly new stars are born and how much material remains available to make planets. It even helps regulate temperature and pressure in the cosmic web, maintaining balance between the regions of high and low density. Without the intergalactic medium, galaxies would run out of fuel. Without it, there would be no slow replenishment of matter, no steady rhythm of cosmic creation. One of the great insights from studying the intergalactic medium is how interconnected everything is. Galaxies may look like isolated islands, but they're not. They're part of a continuous ecosystem, exchanging matter and energy across millions of light years. Every time a star explodes, every time a black hole releases a jet of plasma, every time a galaxy forms a new cluster of stars, it contributes to this grand circulation. The intergalactic medium receives, mixes, and redistributes that energy, shaping the future of the universe. In recent years, simulations of cosmic evolution have become detailed enough to model this process in 3 dimensions. The images that result are extraordinary. They show filaments of gas stretching between galaxies, streams of matter flowing like rivers through the cosmic landscape. The intergalactic medium looks alive, pulsing and moving on timescales of billions of years. You can see where galaxies pull in gas from their surroundings, where supernovae drive it back out, and where the slow tug of dark matter guides its motion. It's a dynamic balance, not chaotic but endlessly shifting, like a slow tide across eternity. As you imagine that, picture yourself drifting somewhere far beyond any galaxy, in the middle of intergalactic space. Around you, nothing seems to happen. No stars, no planets, no visible motion. But if you could wait long enough, millions, even billions of years, you'd see faint currents forming, gas flowing along gravitational lines drawn toward the denser regions of the cosmic web. It would be imperceptible to your senses but visible in the long arc of time, a slow, continuous migration of matter shaping the destiny of galaxies yet to form. The intergalactic medium is also a kind of record of cosmic temperature and density. The patterns in its structure tell scientists when and how the first stars rionized the universe, when galaxies began to pollute their surroundings with metals, and how the large-scale structure of the cosmos evolved. By studying it, we're not just learning about what lies between galaxies, we're uncovering the entire life cycle of the universe itself. There's something beautifully understated about this. The intergalactic medium doesn't announce itself. It doesn't glow in bright colours or form dramatic structures. It's the quiet background against which all other events unfold. But without it, the universe wouldn't hold together in the way it does. The galaxies would be disconnected, their light unanchored, their matter uncirculated. This faint, invisible gas gives the cosmos its continuity. When astronomers map the distribution of this medium today, they find that it extends farther than expected. Even in the most remote voids, traces of gas remain. The density may drop by orders of magnitude, but it never reaches zero. Space, it seems, refuses to be completely empty. There is always something, a particle, a photon, a fragment of plasma, drifting in the dark. That realization changes the way we imagine the universe. It's not a collection of isolated points separated by nothingness. It's a single, continuous whole, connected by invisible matter and energy. Every galaxy, every atom, every patch of space is part of one seamless medium. The intergalactic gas is the connective tissue of existence, holding the cosmos together through the simplest possible means: persistence. So when you think about what lies between galaxies, it isn't just void or distance or emptiness. It's a living environment, faint but real, carrying the traces of everything that's ever happened. The light that travels through it tells us its story. The galaxies that grow within it owe their existence to its quiet flow. The universe itself, vast and old, still breathes through it, a thin, invisible breath that has lasted for more than 13 billion years and shows no sign of stopping. Through the quiet stretches of intergalactic space, past the faint hydrogen gas and the distant glimmer of galaxies, there move things far smaller than stars, far faster than light's familiar companions. The universe, though vast and mostly empty, is never entirely still. Even across the greatest voids, invisible travellers pass, particles born in places of unimaginable energy, racing through the cosmos at nearly the speed of light. They are the cosmic rays, the silent messengers of violent events scattered across space and time. Most of the matter in the universe sits still compared to them. Even stars and galaxies, with all their motion, seem slow beside these microscopic wanderers. Cosmic rays are atomic nuclei, electrons and other high-energy particles that have been accelerated to tremendous speeds by cosmic forces. Supernova explosions, magnetic fields around black holes, and the powerful jets of quasars. They are the universe's restless travellers, never staying in one place, never following a predictable path. Every second, countless cosmic rays pass through the intergalactic medium. Most will continue indefinitely, their journeys stretching across billions of light years. Some will pass through galaxies, their paths bent by magnetic fields. A few will reach worlds like ours, colliding with atmospheres, splitting into cascades of secondary particles before vanishing again. They're invisible to our eyes, but they are everywhere, passing through the empty dark with energies so high that even our best particle accelerators can't match them. The story of how we discovered them begins much closer to home. In the early 20th century, scientists studying the faint electrical charges in the atmosphere noticed something strange. Even in well-shielded detectors, far from any source of radiation, a constant trickle of ionization persisted. It seemed to come from above, not below. When physicist Victor Hess carried instruments aloft in a balloon in 1912, he found that the ionization increased with altitude. Whatever was causing it was coming from space. These mysterious rays, later found to be particles, not rays at all, were the first direct evidence that space itself was filled with invisible, energetic visitors. At first, most cosmic rays seemed to come from within our own galaxy. Supernova remnants, the expanding shells of exploded stars, can accelerate charged particles to near-light speeds through magnetic shock waves. These particles then wander through the galaxy, bouncing from field to field, slowly diffusing through space. The Milky Way is full of them, though they're so sparse we never notice. Each cubic meter of space around you has a few cosmic ray particles passing through every moment, but they're so small and fast that they leave no trace. The higher energy cosmic rays, though, are harder to explain. Some carry energies millions of times greater than any produced by supernova. The most extreme have energies so high that a single particle can strike the Earth's atmosphere with the force of a well-thrown baseball. These are thought to come from the most powerful engines in the universe, active galactic nuclei, quasars, and perhaps even the collisions of entire galaxies. Their origins are still uncertain. Some may even come from outside our visible universe, crossing the cosmic horizon from regions we'll never see. As they travel, cosmic rays interact with everything they pass, with magnetic fields, with stray atoms, with photons of background light. Each collision can change their energy or direction. Over millions of years, their paths become tangled beyond recognition. By the time they reach Earth, they've been deflected so many times that tracing them back to their source is almost impossible. They arrive as whispers from nowhere, carrying hints of everything but the memory of where they began. Even so, scientists have learned to read those whispers. By measuring their energies and the products of their collisions in the atmosphere, we can learn about the processes that created them. Cosmic rays give us information about distant astrophysical events, about the death of stars, the growth of galaxies, and the magnetic structure of the universe itself. They're not just visitors, they're messengers, bringing with them stories from regions we can't see in light. When one of these particles strikes the upper atmosphere of a planet like ours, it sets off a chain reaction. The initial collision produces a shower of secondary particles that cascade downward, spreading through the atmosphere like a faint invisible rain. Some of those particles reach the ground, and a few even penetrate deep underground or into the oceans. On Earth, every second, thousands of these particles pass through your body without harm, leaving no sign they were ever there. The air, the ground, the sea, all are continually touched by the faint aftershocks of cosmic rays that began their journey millions or billions of years ago. It's easy to think of them as intruders, but they're part of the cosmic balance. Without them, the chemistry of the universe would be slightly different. Cosmic rays play a subtle role in maintaining the ionization of interstellar and intergalactic gas, influencing how it cools and condenses. They may even affect the formation of clouds on planets like Earth, though that connection remains debated. Over cosmic time, they've helped shape the chemistry of space, triggering reactions in molecular clouds that lead to the formation of complex organic molecules. If you could see them, if the universe were illuminated not by light, but by the passage of high-energy particles, the sky would shimmer with invisible trails. Every galaxy would be surrounded by a diffuse halo of motion, a constant exchange of energy between stars, gas, and the intergalactic medium. The space between galaxies would no longer seem silent. It would be alive with movement, thin, fleeting, but endless. The intergalactic medium is their highway. Its vast emptiness makes it both a barrier and a passage. Because the gas between galaxies is so thin, cosmic rays can travel enormous distances without colliding with anything. But the same emptiness that allows them to travel also isolates them. Once they leave their home galaxy, they may never return. Their fates are governed by random encounters, a brush with a magnetic field here, a photon there. Some will lose energy over billions of years and fade into the background radiation. Others will cross the entire observable universe and keep going, out beyond where space itself can return their message. Among these travellers are also neutrinos, particles even stranger than cosmic rays. They're so small and elusive that they can pass through entire planets without interacting. Trillions pass through your body every second, streaming from the sun, from supernovae, from the Big Bang itself. They're the ultimate invisible visitors, ghosts that slip through matter without leaving a mark. Unlike cosmic rays, which are charged and easily deflected, neutrinos travel in straight lines from their sources, unaffected by magnetic fields. When we detect one, we're seeing a direct message from wherever it came. Detecting them, though, is incredibly difficult. Because they interact so weakly with matter, most pass through detectors unnoticed. To catch even a few, scientists build enormous observatories, tanks filled with ultra-pure water or ice, buried deep underground or beneath Antarctic glaciers. When a rare neutrino does collide with an atom, it produces a faint flash of light, too brief for the human eye but visible to sensitive sensors. From those flashes, scientists reconstruct where the neutrino came from and what energy it carried. Each one is a data point in the map of the invisible universe. Together, cosmic rays and neutrinos form a hidden layer of cosmic communication. They're not light, yet they tell us about things light can't show. They carry information about violent processes, about explosions, collisions, and decays that happen in places we may never see directly. They're evidence that the universe is always active, even in the emptier spaces. When a massive star collapses in a distant galaxy, for example, it sends out a wave of energy that travels across space in multiple forms: light, gravitational waves, neutrinos, and cosmic rays. Light may fade or be absorbed. Gravitational waves may pass unnoticed, but some of those particles will continue, crossing the intergalactic medium and arriving long after the event itself has ended. Every particle that reaches us is a survivor of cosmic history. These invisible visitors remind us that the universe is not a quiet vacuum, but a medium filled with motion and exchange. Even across the great voids, matter and energy are always flowing. The spaces between galaxies are not barriers, they're part of the same continuous field. Cosmic rays and neutrinos move through them as easily as sound moves through air, except without sound, without friction, without slowing. They're the faint heartbeat of the cosmos, constant and everywhere. It's humbling to realize how much passes through us unnoticed. The Earth is bathed in radiation from the cosmos at all times, most of it harmless, most of it ancient. When a high-energy particle hits the atmosphere, its fragments rain down in silence, unnoticed by anyone. Yet those same particles help us understand where we came from. Some of the isotopes they create have been used to date ancient rocks, to track solar cycles, even to study the history of cosmic activity. In their quiet way, cosmic rays have become part of our planet's story too. Out in the intergalactic medium, away from any star or planet, their presence is even more profound. They contribute to the temperature, the ionization, and the pressure of the space between galaxies. In some regions, they may dominate the local energy density, shaping how gas flows along the cosmic web, Over billions of years, these invisible travellers have helped sculpt the universe, transferring energy from one region to another. Sometimes cosmic rays interact with photons from the cosmic microwave background, producing pairs of new particles and altering the energy distribution of the universe in subtle ways. These interactions are so rare and gentle that they go unnoticed in ordinary experience, but across cosmic time, they matter. Every tiny collision, every transformation adds to the ongoing evolution of space. The intergalactic medium is a stage not of stillness but of ceaseless, invisible activity. There are even higher mysteries among these travellers, ultra-high energy cosmic rays, the rarest and most powerful of all. Their origins remain uncertain. Some may come from the spinning supermassive black holes at the centres of galaxies. Others may arise from processes that occurred only in the early universe soon after the Big Bang. Their energies are so extreme that they challenge our understanding of physics itself. When one strikes the Earth, it delivers as much energy as a falling pebble, concentrated into a single atomic nucleus. These particles remind us that the universe still contains unknown mechanisms of power. They hint that we may not yet understand the full range of what space can do. Somewhere out there, beyond the galaxies we can see, there may be processes unfolding that produce energies greater than anything in our experience. We detect only the faintest echoes, but those echoes tell us that the cosmos is still far from quiet. And so, in the great silence between galaxies, there is motion we can't hear, radiation we can't see, and matter we can't touch. Every second, particles born in ancient explosions race past one another, indifferent to the vastness around them. They have no destination, no boundary. They will continue their journey until the expansion of space itself stretches them beyond reach. Yet their persistence is comforting. They prove that even in the most distant and desolate reaches of the cosmos, there is connection. Energy never truly stops. It moves, transforms, and passes on, linking galaxies and clusters through invisible chains of interaction. The universe may be mostly empty, but it's never still. If you are drifting through one of those intergalactic regions, surrounded by the faint glow of hydrogen and the soft pull of distant gravity, you might think you are utterly alone. But in truth, the space around you would be alive with motion, with cosmic rays streaking by, with neutrinos slipping silently through your body, with photons from distant galaxies sliding past like invisible rain. You wouldn't feel any of it, but it would be there, a continuous reminder that even emptiness is full of passage. And as we keep looking deeper into that emptiness, we continue to find traces of movement that never stops. Particles, waves, radiation, and gravity all intertwined. The cosmic rays and their invisible companions tell us that the story of the universe doesn't end with stars or galaxies. It continues between them, carried on by travellers that never rest, moving through the infinite spaces between everything. There are forces in the universe that move quietly, without light, without particles, and without any visible sign that they exist. They don't shine, they don't scatter, and they don't leave a trace of their passage except for the slightest ripple in space itself. These are the echoes of gravity, the gentle waves that travel across the universe whenever something massive moves suddenly or violently enough to disturb the fabric of space-time. They're not made of matter or energy in the way we usually understand it, yet they carry both. They're the universe's way of whispering about its own motions. The idea that gravity could make waves sounds almost abstract, but it follows naturally from Einstein's theory of general relativity. According to that theory, space and time aren't just passive backgrounds where events happen. They're active, flexible entities that can bend and stretch. When a mass moves through space, it creates a tiny distortion around it, like a ball resting on a soft sheet. When two masses move around each other, that distortion can ripple outward, carrying energy away as gravitational waves. For most of the universe's history, those ripples went unnoticed. They're incredibly weak, even from the most extreme events. It took a century after Einstein's prediction for humanity to detect them directly. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, observed a faint signal that matched the merging of two black holes more than 1 billion light-years away. The detection lasted less than a second, a subtle oscillation in the fabric of space. But it confirmed something extraordinary. Gravity itself can travel in waves. Since then, dozens of gravitational wave events have been recorded. Each one is a message from the darkest, most energetic moments in the universe. The collisions of black holes, the mergers of neutron stars, the slow spiraling deaths of binary systems that end in bursts of space-time vibration. Unlike light or matter, gravitational waves don't scatter or fade easily. They pass through everything, stars, gas, galaxies, without slowing down or losing their shape. That means they carry pristine information from their source, unblurred by the long journey through the cosmos. When two black holes merge, for example, the process releases more energy in gravitational waves than all the stars in the universe emit in light at that moment combined. Yet because those waves spread across so vast an expanse, by the time they reach us their strength is less than the width of a proton. Space itself stretches and squeezes by a fraction of an atom, and yet from that tiny distortion we can reconstruct an event that happened billions of years ago. It's difficult to imagine something so immense and so delicate at once. The energy of entire galaxies carried as a whisper. The collisions of invisible giants, recorded not as light or sound but as the trembling of space. Gravitational waves are, in a sense, the universe's faintest yet most profound form of communication. These waves don't just come from cataclysmic mergers. They're produced whenever masses accelerate, when stars orbit each other, when galaxies collide, even when the universe itself expands. Most are too weak for us to detect, but together, they form a continuous background of gravitational noise that fills space. Astronomers call it the gravitational wave background, a steady hum made of countless overlapping signals from across cosmic history. Imagine it as the faint vibration of the universe's structure, always present, always passing through us. It's not a sound in the air because there's no air between galaxies, but if we could translate it into sound, it would be an endless, low-frequency chorus of events, black holes colliding, neutron stars collapsing, galaxies merging. A deep, omnipresent murmur that began billions of years ago and will continue long after we're gone. Detecting that background is one of the great challenges of modern astrophysics. LIGO and similar observatories can catch individual events, but to hear the cosmic hum, we need larger ears. Instruments that can detect longer, slower waves. Pulsar timing arrays offer one way. Pulsars are rotating neutron stars that emit precise beams of radio waves, flashing like cosmic lighthouses. As gravitational waves pass between us and these pulsars, they slightly alter the timing of their pulses. By monitoring many pulsars spread across the sky, scientists can detect coordinated shifts, the signature of gravitational ripples moving through the galaxy. Recently, hints of that background have begun to appear. The timing of pulsars across vast regions of space shows subtle correlations that match what gravitational waves would produce. It's not yet a complete picture, but it's the beginning of hearing the universe's deepest voice. For the first time, we're starting to sense not just the bright visible cosmos, but the slow rhythm of space-time itself. In a way, gravitational waves connect everything. They're not limited by light's reach, because they travel through space as part of it. When a black hole merger happens in a distant galaxy, the resulting waves ripple outward in every direction, stretching the very coordinates by which distance is measured. For a brief moment, the entire universe participates in that single event, shifting slightly as the wave passes. Even here, on Earth, those ripples move through us, infinitesimal but real, changing the distance between every atom by a tiny fraction. The intergalactic medium, the cosmic web, the dark matter scaffolds. All of them feel these waves. They pass unhindered through gas, dust, and void alike. They are perhaps the purest expression of connection in the cosmos, energy travelling not through matter but through the structure of existence itself. When you think about what that means, it changes how you imagine the universe. It's not a silent, static expanse. It's alive with motion, expansion, vibration, resonance. Every gravitational wave is an echo of movement, a memory of something that happened far away and long ago. We can't see them, but they're always passing through us. The Earth, the Sun, the Milky Way, all are drifting in a sea of invisible motion, bathed in gravitational echoes that never stop. Each detection adds a piece to the cosmic story. When two black holes collide, their mass and spin tell us about how and where they formed. When two neutron stars merge, the resulting wave can reveal the nature of dense matter, how atoms behave under pressures far beyond anything we can reproduce on Earth. Sometimes these mergers also produce light, short bursts of gamma rays or flashes of kilonovae that can be seen with telescopes. When we observe both the light and the gravitational waves from the same event, we get a complete picture, the energy of space-time and the energy of matter speaking together. This new form of astronomy, gravitational wave astronomy, is just beginning. Until recently, everything we knew about the universe came from light, visible, infrared, X-ray, radio, all of it part of the electromagnetic spectrum. But now, for the first time, we're listening as well as looking. We're learning that the universe's deepest phenomena are not always bright. Some are completely dark, detectable only through the ripples they send across the cosmic fabric. And those ripples travel everywhere. They pass through the intergalactic medium, through the voids, through every galaxy and cluster. They carry energy and information, but they don't fade like light does. There's almost nothing that can stop them. Even the most distant, ancient events still leave their mark in the form of gravitational waves travelling outward forever. Somewhere in the darkness between galaxies, those waves continue to move, shaping space in ways that are small but profound. What's remarkable is that space doesn't resist these waves. It simply flows with them. When a wave passes, distances stretch and contract, but there's no friction, no loss. The universe absorbs the energy and carries it onward. If you could watch space-time itself respond, it would look like a calm ocean stirred by a single distant disturbance, the ripples spreading outward endlessly, never quite disappearing. In that sense, gravitational waves are the perfect symbol of cosmic continuity. They remind us that everything that happens, no matter how far away, leaves a trace that touches everything else. The merging of black holes billions of light years away creates a motion that reaches every corner of the universe. The collapse of a single massive star sends ripples that move through every atom of matter. Nothing is entirely separate. It's easy to think of gravity as the quietest of forces, the weakest compared to electromagnetism, or the nuclear forces that bind atoms. Yet on the larger scales, it's the one that shapes everything. It holds galaxies together, governs the orbits of planets, and bends the path of light itself. Through gravitational waves, it also carries memory, a record of motion and change that never fades completely. When scientists first detected those faint ripples in 2015, they translated the data into sound. The result was a brief rising chirp, a faint whoop that climbed in frequency as the two black holes spiraled together. It lasted less than a second, but it was enough to confirm that we had heard the universe move. It was the first time in human history that we had not only seen, but listened to space-time itself. That sound, though derived from data, carried an odd intimacy. It was the voice of the cosmos, compressed into a tone that human ears could perceive. It spoke of distances so great and energies so vast that they defy comprehension. Yet the sound was gentle, almost tender, a reminder that the universe's most violent events can still express themselves in the softest ways. Now, as we continue to listen, we're beginning to map the rhythms of the universe itself, the collisions of black holes, the mergers of neutron stars, the slow dance of supermassive black holes at the centres of merging galaxies. All of them contribute to the gravitational symphony that fills space. It's a music without sound, a resonance that travels not through air but through existence. Even the great cosmic voids, empty as they seem, resonate with these waves. As gravitational echoes pass through, they slightly alter the shape of space, nudging galaxies minutely, changing the distances between them in ways too small to measure directly. Over billions of years, the accumulation of those ripples adds subtle texture to the structure of the universe. The voids themselves act as amplifiers of sorts, channels through which gravitational energy flows freely. If you were floating somewhere between galaxies, in one of those vast dark spaces, you wouldn't feel these waves. They move everything, including you, equally, so there's no sense of motion. But if you had instruments sensitive enough to detect them, you'd see space-time stretching and compressing around you in a slow, rhythmic pulse. You'd be drifting through the quiet heartbeat of the universe. It's a comforting thought that even in the emptiest reaches of space, something is always happening. Not noise, not light, not motion in the way we usually imagine it, but a soft vibration that connects everything. Every event, every collapse, every collision leaves behind a wave, and those waves never truly vanish. They continue onward, filling the cosmos with a kind of invisible memory. So when we talk about gravitational echoes, we're talking about the ongoing story of the universe written not in light, but in motion. These are the vibrations of time itself, the soft tremors that tell us we're part of something vast and continuous. They remind us that even the stillness between galaxies isn't truly still. It's alive with motion too slow to feel, too faint to see, but present everywhere. And as we listen more closely, building instruments sensitive enough to detect the faintest ripples, we're not just studying physics. We're learning to hear the universe as it really is, dynamic, interconnected, and always moving. Every wave that passes through us carries the echo of something ancient, something far away, but also something deeply familiar. Because in the end, we too are part of the same fabric, woven into the same gentle trembling of space and time. Among all the light that fills the universe, the starlight, the glow of galaxies, the background radiance left from the beginning, there is another kind of light, faint and forgotten, drifting in places where it shouldn't exist. It's not attached to any galaxy or cluster. It doesn't belong to any single system. It floats freely, filling the dark spaces between galaxies with a dim and ghostly glow. Astronomers call it intracluster light, but the name barely captures what it is. These are the traces of orphan stars, the ones that have been stripped from their homes and left to wander the intergalactic medium. Their light is difficult to see, almost invisible against the background darkness. It's not the bright light of galaxies or the sharp spark of stars seen through a telescope. It's a soft haze, spread thin across enormous distances, faint enough that it disappears if you try to look at it directly. Only through long exposures and careful subtraction of every other source of light can astronomers begin to detect it. But it's there, a low diffuse glow between the galaxies of clusters, the scattered remnants of countless stellar lives. These orphan stars come from violence. Galaxies do not drift peacefully forever. They move through space like ships in a crowded ocean, pulled and distorted by the gravity of others. When two galaxies pass near each other, their mutual gravity can tear away stars, gas, and dark matter, stretching them into long tidal streams that curl through intergalactic space. Sometimes entire clusters of stars are pulled out, drifting off to become independent systems. Over billions of years, as clusters of galaxies interact and merge, these tidal encounters build up a population of stars no longer bound to any galaxy. In the largest galaxy clusters, this process happens constantly. Galaxies orbit the cluster's centre, colliding and passing through one another, their outer regions stripped by gravitational tides. The stars that escape become unbound, continuing their orbits not around any single galaxy, but around the cluster as a whole. Collectively, they form the intracluster light, a faint diffuse glow that connects the galaxies in a cluster like mist surrounding distant lamps. When astronomers measure this light, they find it accounts for a surprising fraction of a cluster's total luminosity, sometimes as much as 20 or 30%. That means a significant portion of all stars in a cluster are wanderers, no longer part of any galaxy. They drift in the vast spaces between, forming a stellar population that few will ever see directly. These orphan stars aren't all the same. Some are old red giants, stripped long after their galaxies have aged. Others are young, pulled out along with gas clouds that can still form new stars in the intergalactic medium. There are even planetary nebulae, dying stars shedding their outer layers in solitude, and white dwarfs cooling silently between galaxies. Each one is a piece of galactic history, torn loose and set adrift. The light they emit is faint but beautiful in its persistence. Because they're scattered so widely, the glow they produce is diffuse, almost like fog illuminated from within. When astronomers use sensitive instruments to image a cluster for hundreds of hours, the result reveals this soft light spreading outward between galaxies, faint but continuous. It gives the impression that the cluster is wrapped in a gentle halo, a visible sign of all the interactions and collisions that have taken place over billions of years. To detect such light requires patience and precision. Ordinary telescopes are overwhelmed by the brightness of galaxies and the sky itself. Specialized instruments are needed to block out brighter sources and focus on the faintest possible background. Space-based observatories like the Hubble Space Telescope and the newer James Webb Space Telescope have revealed it with more clarity than ever before. In deep images of clusters like Virgo and Coma, filaments of ghost light thread between galaxies, marking the paths of tidal debris, the footprints of ancient encounters. Each faint stream tells a story. Somewhere, long ago, two galaxies passed close enough for their stars to be pulled apart. Some of those stars were thrown outward, some were stretched into long tails, and some fell into the gravitational center of the cluster. Over time, their orbits mixed, spreading them evenly through this cluster's volume. What began as individual acts of gravitational violence became, collectively, a quiet glow. The cluster's diffuse light is a record of all its collisions, preserved in photons that continue to travel long after their sources have been forgotten. For scientists, studying this ghost light is a way of understanding how galaxies evolve in dense environments. The fraction of intracluster light reveals how much interaction and merging has occurred. Clusters with brighter diffuse light tend to be older and more dynamically active, their galaxies having collided many times. In younger clusters, the light is weaker, still forming as galaxies begin their slow gravitational dance. By measuring the colour and distribution of this faint light, astronomers can estimate how long ago certain events happened and how efficiently stars are stripped from their galaxies. There's another layer to the story. Not all orphan stars are created by tidal forces. Some form directly in intergalactic space. When gas is pulled out of galaxies during collisions, it doesn't always fall back. Sometimes it remains suspended in the cluster's gravitational field, cooling slowly and forming new stars of its own. These newborns are truly intergalactic. Stars that have never belonged to any galaxy, born in the thin gas between them. They burn quietly in isolation, their light blending into the faint background glow. Imagine one of those stars, perhaps a young blue star, a few times the mass of the Sun, forming from a stray pocket of gas floating halfway between galaxies. Around it, there are no nearby companions, no neighbouring suns, no visible structures. Just a soft, diffuse glow from distant clusters and the occasional cosmic ray crossing the void. Its gravity binds a few planets, perhaps, but those worlds would never see a bright night sky. There would be no Milky Way overhead, no dense star fields, only the faint glimmer of distant galaxies, each one a silent beacon across billions of light years. Such a place would feel utterly alone, but in reality, it's part of a much larger system. Even in its solitude, the Orphan star is bound to the cluster's gravity, orbiting alongside millions of others that share its fate. Together they form a population large enough to influence the cluster's overall mass and dynamics. Though each one is dim and far apart from the others, their combined light becomes visible when added over vast scales. The cluster's ghostly glow is the sum of countless solitary lives. It's easy to overlook how much these stars tell us about the passage of time. Their presence is proof that galaxies are not eternal. They change, merge, lose pieces of themselves, and leave behind traces in the spaces between. Every diffuse glow is evidence of motion and transformation, the visible memory of how galaxies assemble and evolve. When astronomers model galaxy formation in simulations, they see the same process. Stars flung into intergalactic space by gravitational tides, spreading like dust in slow motion. Over billions of years, those faint trails of light build up, creating halos around clusters and filaments between galaxies. These ghost light is one of the few ways we can actually see how interconnected the universe is. It bridges the gap between galaxies, showing that even their losses become part of something larger. The light doesn't vanish when a star leaves its home. It continues, travelling through space, illuminating the dark between galaxies. Even stripped and scattered, the matter and light remain within the cosmic web, linked by gravity to everything else. Astronomers studying the Virgo cluster, our nearest large cluster of galaxies, have mapped its intracluster light in detail. They've found long tidal streams stretching for hundreds of thousands of light years, connecting galaxies that once passed close to each other. In some cases, these streams are visible remnants of dwarf galaxies that were torn apart entirely. They're stars, now part of the cluster's diffuse glow. In others, they're the aftermath of major mergers, where two large galaxies collided and left behind long tails of debris. These delicate structures, visible only with deep imaging, act like fossils of past cosmic interactions. Over time, these structures fade, the tidal streams disperse, the orbits of orphan stars randomize, and the once distinct trails blend into the general background. The result is a smooth, featureless glow, the final stage of galactic mixing. In the largest clusters, this intracluster light can extend for millions of light years, a faint ocean of photons surrounding every galaxy. From within it, the cluster would not appear as a collection of separate islands, but as a continuous region of soft, diffuse light, punctuated by brighter cores. In a sense, these orphan stars give the universe a kind of quiet continuity. They link the violent past of galaxy formation with the tranquil present. They are the residue of motion, the proof that even destruction can create new beauty. When galaxies collide, stars are born and stars are lost, but light persists. It doesn't disappear, it merely changes where it shines. What makes this light particularly haunting is how near it is to being invisible. Even when we detect it, it's so faint that a single miscalibration, a single trace of scattered light, can erase it from the data. It's a reminder that much of the universe exists right at the edge of perception, not hidden by distance or darkness, but simply by faintness. The ghost light is there all around us, but only the most patient eyes can see it. In the coming decades, new instruments will study this diffuse light in unprecedented detail. Telescopes like the Vera C. Rubin Observatory will map large portions of the sky to faint limits, revealing structures we've never seen before. We'll learn more about how stars are lost from galaxies, how clusters grow, and how much light truly fills the cosmic web. Some scientists suspect that intracluster light extends even farther than we've measured, not just between galaxies and clusters, but along filaments connecting clusters together, creating bridges of faint starlight across the cosmic web. If that's true, then the universe is even more connected than we imagined. The light between galaxies wouldn't just be a byproduct of collisions. It would be a network of faint illumination, tracing the very structure of the cosmos. Each orphan star would be a point of continuity, a tiny contribution to the universe's vast soft glow. There's something profoundly human about the image of orphan stars wandering between galaxies. They began as part of something familiar, part of a system, and then were cast adrift. Yet even alone, they continue to shine. Their light travels outward in all directions, reaching places that will never know where it came from. In doing so, they give shape to the darkness, marking the paths of lost matter and forgotten histories. If you could drift among them, moving slowly through the intracluster medium, surrounded by faint starlight that never gathers into constellations, the scene would feel timeless. Each star would be distant, isolated, its light barely enough to cast a shadow. The background would glow faintly from the combined radiance of countless others. You would be in a place that feels empty, but is filled with motion, filled with the quiet persistence of light. These orphan stars, these ghostly glimmers in the dark, are a kind of memory the universe keeps. They tell us that even when systems fall apart, their pieces remain still shining, still part of the whole. They're not lost, they're redistributed, woven into the vast network that connects everything. Their light, though faint, never truly disappears. It lingers, travelling endlessly through space, adding its own subtle warmth to the cold between galaxies. Out in the deep fabric of the universe, hidden behind the light of galaxies and the quiet glow of wandering stars, lie regions where the rules of space and time bend completely. These are the black holes, the places where gravity becomes so strong that nothing, not even light, can escape. They're the endpoints of matter, the remnants of collapse, the anchors of galaxies, and perhaps, in some strange way, the doorways to other possibilities. We tend to think of black holes as objects, massive compact things sitting in space, but that's not quite accurate. A black hole isn't a thing so much as a region, a place where the geometry of space is twisted inward on itself. It's defined not by what's inside, but by what can't get out. The boundary around it, called the event horizon, marks the point of no return. Once anything crosses that boundary, its fate is sealed. Matter, light, even time itself flow inward toward a singular point, compressed beyond any known limit. The idea sounds impossible, but it's one of the most thoroughly confirmed predictions of general relativity. We've observed stars orbiting invisible companions whose masses are millions of times that of the Sun. We've seen the X-ray flares from gas spiralling into unseen centres, and most strikingly, we've captured images of black holes themselves, or rather their shadows, the dark silhouettes surrounded by glowing rings of light in galaxies far away. The event horizon. Telescope's image of the black hole in M87 showed exactly what Einstein's equations predicted. Space curving so sharply that light itself loops around it before escaping. But black holes are more than cosmic oddities. They are among the most important players in the universe's story. Almost every large galaxy has one at its core, a supermassive black hole millions or billions of times heavier than the Sun. These giants shape their galaxies through their immense gravitational influence. When gas falls toward them, it heats up, creating jets of radiation and particles that can extend for thousands of light years. Those jets, in turn, regulate star formation, sculpting the evolution of the galaxy itself. In this way, black holes don't just consume, they organise. The regions around them are among the most energetic in existence. As matter falls inward, it forms an accretion disk, a swirling ring of gas moving at nearly the speed of light. Friction and magnetic turbulence within the disk heat it to millions of degrees, causing it to radiate intensely in X-rays and gamma rays. Some of that energy escapes along the black hole's rotational axis, forming narrow beams that shoot into intergalactic space. These jets can travel across the cosmic web, carrying energy from the galaxy's core into the intergalactic medium, stirring and heating the gas between galaxies. In that sense, black holes connect the smallest and largest scales of the universe. What happens in their immediate vicinity affects regions hundreds of thousands of light years away. The quiet glow of the intergalactic medium, the temperature of cluster gas, the pressure that shapes galactic evolution, all of these are influenced by the energy released near black holes. They are not simply devourers of matter, they are engines that redistribute energy across cosmic distances. Yet despite all we know about them, the centres of black holes remain mysterious. General relativity predicts that inside the event horizon, matter collapses into a singularity, a point of infinite density and zero volume. Physics as we know it can't describe such a place. It's not just a limit of observation but a breakdown of understanding. The equations that describe gravity, energy and space-time all fail there. Something else must take over. Some quantum theory of gravity that we haven't yet discovered. That mystery has led to speculation, sometimes bold, sometimes restrained. One of the most fascinating ideas is that black holes might not simply be endpoints, but transitions. That they could connect different regions of space-time, or even different universes. The mathematics of general relativity allows for such possibilities, in the form of what are known as Einstein-Rosen bridges, or wormholes. In theory, if space can curve inward sharply enough to create a black hole, it might also curve outward somewhere else, forming a bridge between two distant points. The idea of wormholes has been a favourite of physicists and storytellers alike, because it suggests a way to connect regions of space that would otherwise be forever separated. In practice, though, such bridges would be unstable. Any attempt to pass through would cause them to collapse faster than light could cross. Still, the concept remains an intriguing one, because it reveals something deeper about the nature of space-time, that it might be more flexible and interconnected than our senses can comprehend. In some speculative models, a black hole in one universe could give rise to a white hole in another, a region where matter and energy emerge instead of falling in. If true, this would mean that each black hole might be a seed of a new cosmos, a point where one universe gives birth to another. There's no evidence yet for this idea, but the mathematics doesn't forbid it. It suggests that the cosmos could be part of a much larger structure, a web not only of galaxies, but of universes, connected by hidden bridges formed through collapse. Whether or not such connections exist, black holes already serve as bridges of a kind, not between universes but between eras of time. When we observe them, we're looking at the end of one process and the beginning of another. A massive star collapses, its core compressing under its own gravity until it becomes a black hole. The matter that falls in heats the surrounding space, creating new radiation and motion. Energy flows outward even as matter flows inward. The process transforms what was once a single star into a phenomenon that affects the structure of an entire galaxy. The interplay between black holes and their environments is one of balance. On one side, gravity pulls relentlessly inward, drawing matter toward the event horizon. On the other, magnetic fields and radiation push outward, carrying energy back into the universe. When these forces align, the result can be stable jets that last for millions of years. When they don't, the result is turbulence, chaos, and bursts of energy that ripple through the cosmic medium. Either way, the influence of a single black hole can extend across distances that defy intuition. Some of the most powerful of these are the supermassive black holes at the centres of active galaxies, the ones we call quasars. They're so bright that they can outshine all the stars in their host galaxies combined. From billions of light years away, we can still see their light. That light, in turn, tells us about what's happening in the regions just outside the event horizon. The swirling accretion disks, the magnetic fields twisting into jets, the particles accelerated to near-light speed. Quasars are the beacons of the early universe, showing us what it looked like when galaxies were young and black holes were growing rapidly. As we look deeper into the past, we find that black holes and galaxies seem to evolve together, The mass of a galaxy's central black hole is tightly correlated with the mass of its bulge, suggesting that the two grow in tandem. When gas flows into the centre of a galaxy, it feeds both star formation and the black hole. When the black hole releases energy, it regulates how much gas remains for new stars. This feedback loop continues over cosmic time, linking the smallest scales of gravity to the largest scales of structure formation. It's even possible that without black holes, galaxies as we know them wouldn't exist. Their gravitational influence may help shape the distribution of matter during the earlier stages of galaxy formation. They may act as anchors, stabilizing the systems that grow around them. The energy they release could also drive the chemical enrichment of intergalactic space, spreading elements forged in stars throughout the cosmos. In that way, black holes contribute to the same cycle of creation and transformation that defines the universe as a whole, and yet for all their power, black holes are astonishingly simple in one sense. According to the laws of physics, they can be completely described by just three properties: mass, charge, and spin. All the other details of the matter that formed them, its composition, its temperature, its structure, are lost behind the event horizon. That simplicity gives them an almost perfect symmetry. They are in a way nature's most minimalistic objects, everything reduced to the essence of gravity itself. That simplicity raises profound questions about information. When something falls into a black hole, what happens to the information about its state? Does it vanish, violating one of the core principles of quantum mechanics, or is it somehow preserved in the surface of the event horizon, encoded in ways we can't yet decode? This is the puzzle known as the black hole information paradox, and it remains one of the deepest unsolved problems in theoretical physics. Some theories suggest that information might be stored in quantum fluctuations of the horizon itself, or that it might leak out slowly through what's known as Hawking radiation, the faint emission predicted to come from black holes due to quantum effects. That radiation, though unimaginably weak, implies that black holes aren't truly eternal. Over immense spans of time they lose mass, shrinking slowly until they evaporate entirely. For a stellar mass black hole, this process would take far longer than the current age of the universe. For supermassive black holes, it would take vastly longer still, a timescale beyond comprehension. But eventually, if the theory is correct, even these giants will fade, leaving behind only faint ripples of energy in the cosmic dark. If that future comes to pass, black holes will be among the last active structures in existence. Long after stars have burned out and galaxies have drifted apart, black holes will remain, slowly radiating away their energy. They'll mark the universe's final era, a time when matter, light, and even motion itself have nearly ceased. Yet even then, the story doesn't end. The energy released in their final moments will spread outward, adding to the background glow the faint hum of existence that persists even in near silence. It's remarkable how these regions of absolute darkness can also be sources of connection. Their gravity shapes galaxies. Their energy feeds the intergalactic medium. Their mergers send gravitational waves across the cosmos. And their theoretical bridges, even if they exist only on paper, remind us that the universe might be more deeply linked than we can imagine. In that sense, black holes and the bridges they might form are not opposites of creation, but expressions of it. They're part of the same ongoing process, one that turns collapse into motion and silence into connection. So when we think about what lies between galaxies, we can imagine more than empty space or drifting gas. We can imagine these invisible centers scattered across the cosmic web, each one a node of gravity and energy, binding the universe in ways both physical and profound. They are the unseen hearts that keep the cosmic structure coherent, even across the larger scales. If you could drift far enough from every star, past the faint glow of galaxies, beyond the last scattered atoms of intergalactic gas, you would find yourself surrounded by something we rarely experience in any form: true silence. Not the quiet between sounds, not the stillness we call peaceful, but the complete absence of vibration, the kind of silence that exists only where there is no air, no medium, and no boundary to carry a wave. The universe, in its truest form, is almost entirely silent, and yet it's never still. We tend to think of silence as an absence, but in space, it's more like a background state. It's not that nothing happens, it's that what happens has no sound. The voids between galaxies are filled with motion, with light, radiation, and gravity, but there's nothing there to vibrate. Sound, as we understand it, is a pressure wave in a material medium. Without air, water, or solid matter, there's nothing for sound to travel through. The vast distances of space are perfectly capable of transmitting energy, but not sound. The universe speaks in other ways, in light, in gravity, in the slow rhythm of expansion. When astronomers say that space is silent, they mean that it's quiet to our ears, not to our instruments. Our ears evolved to sense waves of pressure in the range of a few hundred hertz, the kind that travel easily through Earth's dense atmosphere. But the cosmos hums at frequencies far beyond that. The universe vibrates, just not in ways we can hear directly. The soft fluctuations in the cosmic microwave background, the ripples of gravitational waves, the oscillations of stars, even the density variations in intergalactic gas, all of them have frequencies, rhythms and tones, just not in air. In the early universe, before atoms formed, there was no silence. Back then, space was filled with a hot plasma of electrons, protons, and photons so tightly coupled that they behaved like a single fluid. Sound waves rippled through that plasma, real acoustic waves, compressions and rarefactions travelling through the young cosmos. They left their mark in the cosmic microwave background as slight variations in temperature and density. Those primordial sound waves, called Barion acoustic oscillations, are the oldest echoes in existence. They tell us that before silence, there was a kind of cosmic music, vibrations that define the scale of the structures we see today. When the universe cooled enough for atoms to form, the plasma became transparent, and those sound waves could no longer travel. The medium disappeared, and with it, the sound. From that moment on, the cosmos entered its quiet phase. Light continued, but pressure waves ceased. Silence became the natural condition of intergalactic space. And yet, we often speak of the sounds of the universe, the sounds of black holes, of pulsars, of galaxies. These are metaphors, of course. When scientists translate data into sound, they're converting frequencies of light or gravitational waves into a range that our ears can interpret. The results are eerie and beautiful. The chirp of merging black holes, the steady beat of pulsars, the faint hum of cosmic microwave fluctuations. These aren't sounds that travel through space, but sounds that represent its rhythms. When we listen to those conversions, we're not hearing noise, we're hearing structure. Each variation in pitch and tone corresponds to motion, energy, or vibration at cosmic scales. The universe, when translated into our terms, becomes a vast composition, slow, deep, and endless. It's not music in any human sense, but it's a form of order that carries across time and distance. Even though space is silent, it's full of motion that would, in another context, create sound. Stars oscillate, their surfaces pulsing as internal waves move through them. Planets vibrate from impacts and tidal forces. Galaxies rotate, creating gravitational patterns that propagate through dark matter halos. Every one of these is a kind of rhythm, but without air, those rhythms are felt rather than heard. The quietness of space has a strange quality to it. It's not empty quiet, but full quiet. A quiet filled with light, energy, and motion that never breaks into sound. If you could somehow experience it directly, it might not feel like absence at all. It might feel like calm, the kind of calm where everything moves but nothing interrupts. The galaxies would drift silently past, their light crossing the void without echo or noise. Even the most violent explosions, supernovae, black hole mergers, gamma-ray bursts, would unfold in perfect silence. Their radiation would travel outward, their gravity would ripple through space-time, but there would be no sound, no shock, no roar, only light, only motion. When you think about it, that kind of silence isn't empty, it's patient. The universe doesn't rush to announce itself. It doesn't fill the void with sound or chaos. It simply exists, letting its energy move in ways that don't require a voice. That quiet has endured for nearly 14 billion years, and in it, every event leaves its mark, not in sound, but in form and motion. On Earth, we're surrounded by sound constantly. The air vibrates, the ground carries low rumbles, even silence here is filled with the faint hiss of life. It's easy to forget that this is rare. In almost every other place in the universe, there is nothing like that. The quiet of space is so deep that even a small noise, the hum of an airlock, the buzz of equipment, would seem enormous against it. Astronauts who have floated outside the International Space Station describe it as both peaceful and strange. They see the Earth, the stars, the glow of sunlight on metal, but they hear nothing. Even the most familiar motions, like moving a hand or turning a head, produce no sound. The world feels divided, half seen, half felt, entirely still. But that silence is not lifeless. It's filled with signals waiting for instruments to interpret. Every patch of sky contains radio waves from distant galaxies, microwaves from the early universe, X-rays from hot gas, and faint gamma rays from decaying particles. When these invisible vibrations are translated into data, the silence comes alive. The universe begins to speak in numbers, in frequencies, in patterns. It's a kind of conversation, just not in sound. Even gravitational waves, those ripples in space-time, have frequencies. They are the truest form of cosmic vibration, waves not in air or matter, but in the geometry of the universe itself. When detectors like LIGO or Virgo capture them, the signals are so faint that they must be amplified thousands of times. When converted to audio, they become brief chirps or deep, distant booms, the sound of two black holes merging, of two neutron stars colliding. Those sounds aren't carried through space, they're the Earth's response to a passing ripple. It's as if space-time itself shivered for a moment, and we felt it. If space could have a voice, it would be these vibrations. Not loud, not sharp, but continuous. A whisper so deep it becomes structure, a hum that defines the scale of everything. The cosmic microwave background, for instance, is often described as the afterglow of the Big Bang, but it's also a record of the universe's early vibrations. It's not silence frozen in time, it's the fossil of sound, the last echo of a universe that once resonated like a drum. When we convert that radiation into audible tones, we hear a low, steady hiss, not random, but structured. It carries the imprint of those early oscillations, the pattern of density and temperature that gave rise to galaxies and clusters. The universe began, in a sense, with sound, and then gradually fell into silence as it expanded and cooled. That silence, far from being empty, carries memory. Every photon of the background radiation, every ripple of gravity, every faint vibration of matter is part of that ongoing record. It's easy to imagine the silence of space as lonely, but in truth, it's deeply connected. The absence of sound allows other forms of communication to exist. Light travels farther than any voice could. Gravity reaches everywhere. Even in the quietest void, the universe is full of interaction. Photons meeting particles, dark matter shaping space, energy flowing from place to place. The silence makes room for these other exchanges. If you could somehow stand at the edge of a galaxy cluster and listen, not with ears, but with instruments that could translate every wavelength and vibration into something you could perceive, you would hear a vast spectrum of motion. The radio hum of charged particles spiraling through magnetic fields, the flicker of X-rays from hot gas, the distant gravitational murmurs of merging black holes. It would sound less like noise and more like a slow, endless pulse, the heartbeat of structure itself. But our senses, evolved for the narrow world of Earth, are deaf to it. We hear only air and the universe has none. The cosmic silence isn't a flaw, it's a feature. It allows the immense range of energy and motion to exist without interference. It's the reason light can travel across billions of light years without distortion. It's the reason galaxies can move in perfect arcs. Silence, in this sense, is the foundation that makes the universe coherent. The idea that silence and motion coexist so completely can be strange to imagine. On Earth, movement and sound are linked. Every vibration creates noise, but in space, they're separate. Motion doesn't require sound. It exists purely in geometry and energy. The universe doesn't need a medium to carry its rhythms, it is the medium. That's why scientists sometimes speak of the music of the spheres, not as a literal sound, but as an ancient intuition that the cosmos has order, proportion, and harmony even in silence. The orbits of planets, the oscillations of stars, the frequencies of gravitational waves, all of them are patterns, repeating and predictable, forming a kind of silent symphony. It's not a sound we can hear, but it's one we can describe, measure, and translate into understanding. When we listen to space through our instruments, what we find isn't chaos, but rhythm. The universe doesn't hum randomly, it vibrates with structure. Galaxies rotate in steady cycles. Pulsars spin with perfect regularity. Quasars flicker in patterns that repeat over years. Even the expansion of the universe follows a steady accelerating curve. It's all motion, all vibration, all silent music. If silence has a texture, the universe would be its grandest example. It's a silence woven from time, filled with motion, and sustained by balance. It's not the silence of absence, but of completeness, a kind of equilibrium that allows everything else to exist. In that quiet, stars are born, galaxies collide, and black holes merge. The silence doesn't stop any of it. It carries it. Sometimes, when scientists compress data from telescopes into sound, the results surprise even them. The frequencies of galaxy clusters, when translated, become deep, droning tones. The oscillations of stars produce clear, bell-like notes. Each one has its own signature. These aren't sounds made by space, but representations of its structure. The patterns that exist whether or not we can hear them. It's strange, then, that in our search to understand the universe, we often return to metaphors of sound. We talk about echoes, waves, vibrations, harmonies. Even though the cosmos is silent, we describe it in the language of hearing. Perhaps it's because hearing is how we experience continuity, how we sense time. Light gives us the shapes of things, but sound gives us duration. And the universe, for all its stillness, is about duration, about things unfolding across time. If you were to drift endlessly through intergalactic space, through that perfect silence, you would not feel isolated. You would feel surrounded by motion too slow to sense, by light too faint to see, by gravity too gentle to notice. The silence would not be an absence, but a medium, the quiet in which everything else happens. And if you could listen in the right way, you might realize that the silence itself is a kind of conversation, an ongoing dialogue between energy and emptiness, between motion and stillness. The sound of silence in the universe, then, is not something we can hear, but something we can understand. It's the steady background against which everything else plays out. It's the calm that allows light to travel, matter to form, and time to flow. It's the space that holds the story, not by filling it, but by letting it unfold. And as we continue our journey through the dark, quiet cosmos, this silence follows us. Not empty, but vast, patient, and full of hidden rhythm, waiting to be understood by those who can listen without needing to hear. After drifting for so long through the vastness of the cosmos, across galaxies, through invisible threads of matter, through waves of gravity and silence itself, it can feel strange to turn the view back toward something small, to step away from the immensity of the intergalactic web and consider the human scale. This single planet, this brief life, this narrow slice of experience, and yet it's the only scale from which we ever perceive the universe. Everything we know about distant galaxies, black holes, and the expansion of space is filtered through the limits of human senses, human tools, and human imagination. We are small, but through understanding, we reach outward farther than our size would ever suggest possible. When you look up at the night sky, you see light that's travelled unimaginable distances. You're standing on a planet orbiting a modest star in a spiral arm of a galaxy among hundreds of billions of others, all held together by invisible matter and energy. Yet the act of looking, of observing, thinking, wondering, connects you directly to that immensity. The light that enters your eyes carries information about events that happened before humanity existed, before Earth existed, before even the sun had formed. That connection, fragile as it seems, places us in the centre of understanding, even if not in the centre of the universe. The scale of the human world is defined by what we can touch, feel, and measure with our bodies. A few meters, a few kilometers, maybe a few thousand. We think in terms of hours and days, not billions of years. Yet the physical laws that govern the fall of an apple or the swing of a pendulum are the same ones that shape galaxies and determine the fate of the universe. The same gravity that holds you to the Earth governs the motion of stars. The same thermodynamics that describes how heat moves through air also describes the birth and death of stars. We're made of the same matter, following the same rules, part of the same unfolding story. It's easy to feel small against the cosmic scale, but size alone doesn't determine significance. The universe is vast, but it's indifferent. Meaning doesn't emerge from scale. It emerges from awareness. The ability to observe, to ask questions, to interpret light and motion. That's what gives structure to experience. The cosmos would continue without us, but without consciousness, there would be no understanding of what it is. We are, in a sense, the universe becoming aware of itself. The human brain is a structure of staggering complexity, built from atoms that were once forged in ancient stars. Those atoms, carbon, oxygen, nitrogen, iron, once drifted through interstellar clouds, perhaps part of the very intergalactic medium we've described. Over billions of years, gravity gathered them into new systems, new worlds, and eventually into life. Each neuron that fires inside your mind is the descendant of a process that began in the heart of a star. Every thought, every memory, every moment of awareness is an echo of the universe's early moments, condensed into a structure only a few kilograms in mass. That contrast between scale and understanding is one of the most beautiful aspects of existence. The universe operates across distances and times we can barely imagine. Yet the same laws that shape galaxies also allow molecules in a brain to form thoughts about them. From the human perspective, we stand at the intersection of the smallest and largest scales. We can look inward, toward the quantum and atomic, and outward, toward the cosmic and infinite. Both directions lead to the same mystery: how complexity arises from simplicity, how structure emerges from the basic ingredients of matter and energy. When scientists measure the universe, they use numbers that stretch far beyond normal experience. A light year, for instance, is nearly 10 trillion kilometers. A billion light years is a distance so large that even light, travelling at 300,000 kilometers per second, would need a billion years to cross it. Against that background, the human lifespan, perhaps 80 years, is almost nothing. Yet in that short time, we have measured the age of the universe, mapped the galaxies, detected gravitational waves and photographed black holes. We've turned curiosity into an instrument powerful enough to reach the edge of the observable. It's worth pausing to consider what that means. The atoms in your body, assembled into cells, into tissues, into a living person, are arranged in a way that allows you to perceive and understand the very forces that created them. You can trace your existence back through generations, through evolution, through planetary formation, through the birth of the sun, through the collapse of interstellar clouds, all the way back to the first few minutes after the Big Bang. In a very literal sense, you're made of the universe's memory. And yet, for all our insight, we still experience life at a human pace. Time flows for us in heartbeats and breaths, in the turning of days and the passing of seasons. Cosmic time moves differently. Galaxies evolve over billions of years. Stars live and die over spans that dwarf human history. Even the speed of light, the fastest possible motion, seems slow when stretched across cosmic distances. The light from a distant galaxy may travel for billions of years, only to end its journey in a single instant when it strikes your eye. To that photon, the universe might as well have no age at all. From that perspective, our scale isn't wrong. It's simply one point among many. The universe contains everything from the subatomic to the galactic, from Planck lengths to megaparsecs, from attoseconds to eons. We inhabit a narrow middle ground, large enough to perceive, small enough to think. In that middle ground, complexity flourishes. Molecules can interact, chemistry can take place, biology can emerge, and consciousness can evolve. The human scale is where the universe becomes personal. Even our technology reflects that balance. Telescopes stretch our vision outward, microscopes inward. The same physics governs both. The same mathematics describes both. We've built instruments that allow us to see what no eye could see, to hear what no ear could hear. When you look at an image of a distant galaxy cluster, or a field of stars taken by the James Webb Space Telescope, you're not seeing it with your eyes alone. You're seeing through centuries of accumulated understanding, through lenses, mirrors, sensors, equations and theories, all built by hands and minds that evolved on a small, rocky planet orbiting an ordinary star. That smallness is not a limitation, it's a perspective. From where we stand, we can see the largest structures in existence and infer the smallest particles that form them. We can measure the expansion of the universe, the motion of galaxies, the temperature of the cosmic microwave background, and still be moved by the sight of sunlight reflecting on a drop of water. The human scale connects the infinite with the immediate. There's a quiet symmetry in the way our senses work. We see only a narrow band of the electromagnetic spectrum, yet within that band lies the full range of colours that fill our world. We hear only a limited range of frequencies, yet within it we find the richness of music and speech. Our experience is finite, but our imagination expands it endlessly. That imagination, that ability to build models, to ask questions, to picture what we cannot touch, is what makes our scale meaningful. Even in the context of the universe's age and size, the human story is remarkable. In just a few thousand years, we've gone from staring at the stars with wonder to understanding how they shine. We've learned that the Earth is not the centre of the universe, and that the Sun is one of countless stars, and that those stars form galaxies that stretch beyond number. We've discovered dark matter and dark energy, forces that make up most of existence but remain invisible. Each discovery expands the boundary of what we know, yet each one also deepens the mystery. The more we learn, the more we realise how much lies beyond our reach. And yet, even the unreachable becomes part of our awareness. We can't travel to another galaxy, but we can understand its light. We can't witness the birth of the universe, but we can detect its afterglow. Knowledge turns distance into intimacy. The universe may not know we exist, but through observation, we make it known. At the human scale, meaning and mystery coexist naturally. We're built to live on a planet where gravity feels constant, where the sky curves overhead, where a lifetime seems long. We carry within us instincts shaped by survival, but also curiosity shaped by wonder. When we study the cosmos, we bring that same mixture with us. Practical, fragile, searching. The questions we ask are simple, but their answers open into infinity. It's easy to imagine that our smallness makes us insignificant, but smallness is relative. From the perspective of a subatomic particle, we're vast. From the perspective of a galaxy, we're brief. Yet from the perspective of awareness, we're exactly the right size to understand both. The human scale is where comprehension happens, where the immeasurable becomes measurable, where the unknown becomes knowable. Every piece of knowledge we hold, every constant, every law, every measurement, has been built within the limits of human perception. We measure time in seconds, distances in meters, mass in kilograms. But those units are inventions, ways of translating the universe into terms we can grasp. The universe itself doesn't care about our measurements, but it allows them to work. The regularities we find, the constancy of the speed of light, the stability of atoms, the predictability of motion, are what makes science possible. They're also what make existence stable. And even though our understanding is incomplete, it's not wrong. Each discovery refines the picture, adds precision, deepens context. The human scale is not about having the full truth. It's about being part of the process of uncovering it. We're not outside the universe observing it. We're inside it, made of it, and thinking about it from within. That recursive loop, matter that studies itself, might be the most extraordinary structure of all. If you imagine the universe as a continuum, stretching from the quantum foam at the smallest scales to the cosmic web at the largest, then the human scale lies at a point of balance in between. It's the region where complexity peaks, where physics becomes chemistry, chemistry becomes biology, and biology becomes thought. It's where atoms can form systems stable enough to evolve, where time flows slowly enough for life to change, and where awareness can look outward and ask why. That balance is fragile, but it's also enduring. For billions of years, the universe expanded, cooled, and structured itself until the conditions for life became possible. On one small world, that life began to think, to measure, to record, and to wonder. In the span of cosmic history, humanity is new, a brief, flickering moment, yet within that moment we've built an understanding that reaches back to the beginning of time. Perhaps that's what makes the human scale so special. It's not its size, but its relationship to everything else. We exist at the intersection of knowledge and mystery, small enough to feel wonder, large enough to seek understanding. We can look up and see galaxies billions of light years away, and we can look inward and find universes within a single cell. The scale of the human world is not a limitation. It's the doorway through which the universe perceives itself. And as we continue drifting through space, orbiting an ordinary star in an ordinary galaxy, we remain part of the same story as everything else. The same matter, the same forces, the same patterns. From the largest supercluster to the smallest thought, it's all connected. The human scale is not separate from the cosmos. It's one of its natural outcomes, a momentary expression of its endless process of becoming. It's a strange thing to speak about the universe for so long, to drift through the light of galaxies and the silence of voids, and then to arrive back here, to the quiet space between wakefulness and sleep. We've wandered far, across billions of years and uncountable distances, yet the return is simple. You, lying there, listening in the dark, are still part of the same universe we've been describing. The same forces that move the galaxies move through you. The same atoms that built the stars now rest in your body. The same silence that fills the spaces between clusters surrounds you now, soft and steady. When we began, we asked what lies between galaxies, the vast stretches of apparent nothingness, the darkness that seems to separate everything from everything else. And we've learned that the answer isn't nothing at all. It's filled with light too faint to see, with matter too thin to touch, with energy too quiet to feel. It's filled with the slow expansion of space, the low hum of gravity, the faint whisper of radiation left from the beginning of time. What lies between galaxies is the same thing that lies between thoughts, between moments. Connection. A fabric that never truly empties no matter how far it stretches. You could call it stillness, but it's not the stillness of rest. It's a dynamic quiet, a kind of equilibrium that lets everything else exist. Stars form and fade, galaxies drift apart, matter cycles through creation and decay, but the background of it all remains constant, wide and patient. The universe doesn't need to hurry. It has all the time there is. When you close your eyes, what you experience as darkness isn't empty either. It's full of faint light still reaching you from everywhere. Light that began its journey long before there were eyes to see it. Every photon carries history. Every trace of energy a memory of something that once was. The darkness that surrounds you now is full of ancient messages, moving silently through space, indifferent to time. You're always within that field of light, even when you can't perceive it. If we could remove all the noise of our own existence, the hum of technology, the weight of atmosphere, the heartbeat of our planet, and simply float in the intergalactic void, we would find a quiet unlike any other. No wind, no echo, no sound at all. And yet it wouldn't feel empty. There would be a faint glow in every direction, a barely perceptible background from the first light of the cosmos. It would be like floating in the memory of creation. That's what the universe looks like when everything else is stripped away. A calm sea of old light, stretching infinitely, timeless and slow. It's strange to think that our own lives, our breathing, our thoughts, are part of that same continuum. The energy that animates a living body is not separate from the energy that drives the stars. The chemistry that keeps you alive is the same chemistry that unfolds in distant nebulae. Life is just one of the universe's many experiments in complexity, a way for matter to become aware of its own existence. And consciousness, that fragile awareness that flickers in your mind, is one of the few things capable of holding the whole picture at once, the smallness of our lives and the immensity of everything beyond. When you let yourself sink into that thought, something quiet happens. The distance between the personal and the cosmic begins to fade. The universe doesn't feel far away anymore. It feels immediate, present. Not something you look at, but something you are inside of. Every breath, every pulse, every slow rhythm of your body mirrors the rhythms of the cosmos. The expansion of your lungs, the contraction of your heartbeat, the slow cycling of air and warmth. All of it echoes the greater cycles outside, the collapse of stars, the flow of energy, the expansion of space. You're not separate from it. You never were. For most of human history, the night sky has been our mirror. We looked up, saw patterns, and found meaning in the lights that seemed to hang there, far beyond our reach. Now we understand that those lights are other suns, other systems, other galaxies. That understanding hasn't made the sky less beautiful, it's made it deeper. Each point of light is a window into the past, each faint glow a message from another time. When you look up, you're seeing not just space but time itself, stretched, delayed, preserved in light. Some of that light began its journey before the Earth even formed. Some of it left its source before the atoms that make up your body existed. And now here it is, entering your eyes, completing a story billions of years long. You are the ending of that light's journey, at least for now. You are part of its story just by perceiving it. There's something grounding about that thought. The universe, for all its immensity, is not unreachable. It's already here. It's within and around us all the time. Every atom in your body was once part of something older, a star, a planet, a cloud of gas. You're built from recycled starlight, from the dust of generations of cosmic events, the calcium in your bones, the iron in your blood, the oxygen in your lungs. All of it was born in the nuclear furnaces of ancient stars. You are, quite literally, made of what you observe. That connection doesn't need to be mystical to be profound. It's physics, chemistry, biology, the natural flow of matter and energy through time. But knowing it changes how we feel about the dark. The space between galaxies isn't just a cold emptiness. It's the origin of everything we know. It's the quiet field where energy and matter interact, where stars are born, where gravity sculpts, where light travels endlessly. It's the background that makes life possible. And here, on this small planet orbiting a star at the edge of a galaxy, that same background hums beneath our existence. The night sky above you right now, whether clear or clouded, is part of that same structure. You don't have to go far to find it. You only have to be still enough to notice it. When the world quiets and you let your mind drift, that's when the distance between the stars and your own thoughts starts to disappear. The same calm that fills the spaces between galaxies begins to fill you too. The worries of scale, the feeling of being small or temporary, fade into perspective. You don't need to be large to belong to something vast. You only need to exist within it, and you already do. In that sense, sleep and the universe are not so different. Both are forms of surrender. In sleep, you let go of awareness and allow your mind to drift through its own internal space without control, without boundaries. In the universe, everything does the same. Matter drifts, energy flows, gravity guides, without resistance or effort. The cosmos doesn't struggle to exist. It simply continues. Sleep is the same quiet continuation, but within consciousness. As you drift now between thought and rest, you might imagine yourself floating not in a room, but in space, not in the cold and emptiness of the void, but in the quiet and warmth of connection. Around you, light from distant galaxies moves silently, stretched by expansion. Faint hydrogen clouds glow softly in the background. The dark matter web holds everything in its delicate lattice, and you, a small consciousness within it, drift peacefully, part of the same balance. You don't have to understand all of it. You don't have to measure or explain. The beauty of the universe isn't only in its logic, but in its existence, in the simple fact that it is, and that you are within it. The atoms that make you, the thoughts that form you, the calm that settles over you now, all are expressions of the same laws, the same unfolding pattern. Somewhere, beyond what we can see, new stars are forming. Somewhere else, old stars are fading, returning their matter to the cosmic sea. Galaxies are drifting farther apart, the fabric of space stretching with every passing moment. It all continues, endlessly, silently, beautifully, and you, in this small moment of rest, belong to all of it. The distance between the stars is vast, but the distance between them and you is only a thought. The same forces that govern them govern you. The same calm that fills the universe can fill your mind now, slow and steady, deep and clear. There's no rush, no urgency, no need to hold on to anything. Just the quiet rhythm of existence, inside and out, perfectly aligned. As you breathe, imagine that your breath carries the same rhythm as the universe's expansion, slow, steady, effortless. Each inhale gathers the world in, each exhale lets it drift. Somewhere countless light years away, galaxies are doing the same, moving apart and together in slow motion, carried by invisible forces. The rhythm is the same, only the scale is different. Let that thought rest in you. Let it settle as softly as starlight. The universe is vast, yes, but it's also here, within you, around you, connected in every direction. You're not apart from it. You're part of its continuity, matter and energy, thought and stillness, all in one unfolding field. So as you drift towards sleep, think of it as another kind of journey, not away from the universe, but deeper into it. The quiet that fills your mind is the same quiet that fills the spaces between galaxies. The calm that spreads through your body is the same calm that holds the cosmos in balance. Everything that exists, every atom, every photon, every drifting galaxy, moves within that same balance, and now you do too. Let the silence widen. Let the distances grow soft. Let the light fade into memory. The universe continues, patient and infinite, and you, between the stars and sleep, continue with it, quietly, effortlessly, beautifully. Thank you for drifting with me through the quiet tonight, through the light, the dark, the distances, and the stillness between. You've listened across time itself, across the fabric of the universe, through places no voice can truly reach. And yet here we are, sharing the same calm, the same silence, the same moment of being. This is what Science for Sleep has always been for. A way to let wonder slow down, to let the mind rest inside something larger than thought, to remind ourselves that curiosity and calm can live in the same breath. If this helped you find a little peace, a little perspective, or a little sleep, you can stay with me again next time. There are always more questions waiting quietly out there, and we'll keep exploring them, softly, patiently, together. For now, you don't need to think about galaxies or time or distance. Just breathe. The universe is still here, the stars are still shining, the silence is still carrying everything forward. Good night, and sleep well under the same sky that began it all.